Alright. So the exercise I'm going to work out on the board here is about how we get the Robertson-Walker metric, how we derive it. And the way it's, one way of doing that is by modeling the universe as a three-dimensional surface on a four-dimensional sphere it was, which I'll show you in a second. Shall I first start by writing down the metric again so that we know what we're working towards? Right? Alright, so this is the metric, and there is an equation in the book that I used that helps in creating this this metric. And let me see, where is it? Yeah, this is the one. This equation that says something about the line element in Robertson-Walker metrics. It says it is equal to just this. This would be in C is 1 coordinates then, I guess. That times this other element. This in itself is also a line element, but this is just a spatial one, not a space-time element. And this is the one I'll show you how to derive. As I said, I'll be talking about spheres, four-dimensional spheres. The way they're defined is a little bit different than, well, actually only very little different from three-dimensional spheres. Three-dimensional sphere is defined as such is equal to a number. This is always true for spheres. And if you want to extend this to an extra dimension, you just add another letter to this equation. There. In the derivation I am using, this r was just called 1, which I'll just keep on doing as well right now. And let's see, just like you regularly can do with a sphere, you can switch this coordinate system from being a Cartesian coordinate system to a polar coordinate system. In this case, the expressions for all these variables would look a little more complicated than they usually would. We introduce actually a pretty poor choice of letters. Let me just think for a bit. Let's just call this angle psi or something like that. And cosine of phi. This third angle is just a different angle that is necessary in 4 dimensions to move from Cartesian to polar coordinates. Similar. Oh, and the r would usually be here, but since we set the r to be 1, you don't see it here. Here we have and then this last one would be just this. Okay, just like what you can do with three-dimensional polar coordinates is that you can calculate their differentials, square other differentials, and add them together to get basically a line element for the surface of a sphere. On a three-dimensional sphere, that would then be, see, what you would get for that is, let's see, squared. And similarly for a four-dimensional sphere, this spatial line element would be that there. And this is something you can just substitute into this Robertson-Walker spacetime metric here. So if you would do that, you'd end up with dt squared taking some things outside the brackets here as well. Oh, wait a second. Seems like I'm missing something here. Yes, I am missing something, I think. Yeah, this one is a little more complicated than it is as I wrote it just there. I think this one is supposed to be like this. And this one, if you take some things outside the brackets of this one, that times d theta squared plus that would be your line element. Derivations like this you can also make for flat spacetimes and hyperbolic spacetimes, so for the other two options of Robertson-Walker metrics that exist. And then it would have similar forms to this one. They would actually be almost entirely the same. Although it would be different would be this element over here. If you would do the same derivation for a flat spacetime, that factor there would be, let's see, where is it? Just that number psi there, and in a hyperbolic, universe, that factor would be inverse sine or sine h of that number.
The first sine is not a sine h.
Oh, sorry. That's my bad then. Hyperbolic sine, I mean. Yeah. Yes, hyperbolic sine. Not
you sure that you mean hyperbolic sine?
Yes.
Not inverse sine? Okay.
Yep.
Just making sure before we have.
Yeah, it was just.
Okay.
Oh, and this should also be squared then. Okay.
Like, so will you have sine of the hyperbolic sine of psi, or will you just replace
no,
the
this
sine?
the whole term here will be replaced by this. So sine squared psi would be replaced by sine h squared psi.
Oh, right. So at the moment you assume that we're in a flat, in a spherical universe with the normal sine on.
This would hold for a spherical universe. I'll write that down here as well then. That is word for a spherical universe. Okay.
Can I ask one as well?
Mm-hmm.
Continue. You say that at the moment that you derive this for hyperbolic universe, then the sine squared is replaced by a hyperbolic sine squared.
Mm-hmm.
What have you changed in your initial setup? Because the lower part, the left lower part of the board that you've used right now, where you say w squared with x plus y squared z squared equals r squared, or 1.
Mm-hmm.
From this, you get your x, y, z's, and w's and their differentials, and you can derive this line element.
Yes.
How would that change for hyperbolic universe?
That is something I haven't worked out. This is just a result I found in the book.
Okay.
If I'm being completely honest. There is some other derivation I found online that basically doesn't even use this method of derivation, use a different method, with which you don't even actually have to deal with things like this. So if you want I can show you that, but how exactly this comes out of here, that's something I don't know, sadly.
Okay. Just to give you a hint,
Mm-hmm.
for everybody, what Nelson here did, I will let you continue in a second.
Yeah,
Because
it's fine,
I
it's fine,
want
fine.
to make sure that this is all settled. What Nelson here did was that he say, well, a four-dimensional sphere is by definition w squared plus x squared plus y squared plus z squared equals r squared. This is the definition of a four-dimensional sphere. Even it's hard to envision this visually, but that's the mathematical definition. There's also a definition for a four-dimensional hyperboloid.
Mm-hmm.
So his start equation, w squared plus x squared plus y squared plus z squared equals r squared, would be a different equation. From that moment on, the steps will be similar, will be exactly the same. It's just that in that starting definition, there will be something different.
Yeah.
And yes, if you then continue with the method as he explained for the spherical universe, you would indeed get hyperbolic sine squared.
Instead of sine squared there.
Yes, exactly.
Now, here directly comes another step that I didn't fully understand. I've been trying to work out why this is being done, but I just sadly couldn't find anything in any source that I looked up. That is that it is said that this sine squared psi here, or that psi there, or that sine h squared psi there, depending on what universe you choose or what the universe you decide to look at, either one of these, actually was replaced or defined to be something like that, to be a radial component instead of something angular.
Yes.
Why that is done, I sadly couldn't figure out, like I said, but I'll just assume for that to be true for now. If, for example, continue with the spherical case, let's just write this. You define r to be equal to sine of psi, and what you can then do is, I have to take a good look at it. Wait a second. Oh yes. What that would immediately do is you can just square both sides of this. Get that. You could then replace the sine squared psi term for r squared here, and that would immediately give you already two of the parts of the metric. If this would be an r squared, you would have r squared d theta squared multiplied by this a squared t there, which would correspond to this part of the metric. This term here is multiplied through this a term here and the r term here by d theta squared. So you already have one part of your whole metric in there if you make the substitution. Same would apply to this one. You would end up with r squared times sine squared theta times d phi squared, and there's also still the a squared there, which would correspond to this metric element. This one is still a bit of a mystery, but that one will just roll out of calculating the differential of psi and then squaring that. It's also a derivation I did, so then you would end up with, let's see, cos of psi times d psi.
Where did you get that from?
That's just by calculation. If you
I
take
see.
the differential of both sides, this is what comes out. Yep. Oh wait, well no wait, there should be a... Wait a second. I'm missing something here. Oh no, no, it's not true. You can rearrange this for the psi. It should then be dr over cos psi. And then you square that to get cos squared psi, which you can also express as by some trigonometric identity as 1 minus sine squared over psi. We just defined sine psi to be r. So then what comes out is that the differential of psi squared is just equal to differential of r squared divided by 1 minus r squared. If we go back to the metric for a second, we have the k factors in there. They are the curvature factors. These curvature factors, as we've seen, will describe what kind of universe you're looking at. If you would go for a spherical universe, this k factor would be 1. So then this term will basically become a squared t over 1 minus r squared. 1 minus r squared is there. The a squared t comes from here. So in that case, you would have the right metric element for this one as well. And the last one, minus 1, kind of rolls out the I'm not sure if it's a definition or something, if it's derived as well. Comes out of just the line element of general Robertson-Walker metrics. Because you have your minus 1 there. That one is the one over there. What I can do is do some similar derivation to this one, but then using the flattened hyperbolic scenarios. And I can then show that the this metric element would still come out as the right one. Shall I do that, or is it something we can just assume to be true?
I know the answer, so
Okay.
don't look at me.
Shall I show you?
Yeah, sure.
Okay,
Wait, I have a question.
sure.
So what does that psi represent?
Psi is just a third angle that you would have to introduce
Oh, because the
for spherical coordinates
okay.
in 4 dimensions.
And in 4 dimensions, the sine of that angle would be the radius.
Yeah, that's some part I tried to figure out, but I couldn't find the answer anywhere,
Which is
sadly.
interesting.
Yeah.
Well, the good thing is it's already in the board.
Oh, that's nice.
Because you have the w squared plus x squared plus y squared plus z squared equals r squared. And you have your x, y, and z and w's. If you
Mhm.
plug that in, you will find that r equals the sine of psi.
Oh, okay, is that it?
Oh.
Interesting.
It's already there.
Oh, okay, so that's it.
So it's not a mystery where the thing comes from. It's very,
Yeah, well, it's not a
literally
mystery
by
where the thing
definition
comes from, it's a bit of a mystery finding out why, like, how to get there.
Yes.
Sorry,
Yeah.
can you repeat it? Where is it?
Yes, Nelson wrote down what the definition is of a 4-dimensional sphere.
Yeah.
And he also wrote down what the x, y, z, and w are. At the moment that you plug that in, and you just multiply your cosines and your sines and your cosines, all these x, y's, and z's in terms of the new angles, you will find that some particular combination of cosines and sines of all these angles equals r squared.
Oh, okay.
And that is exactly r is sine psi.
Okay,
So
that's one mystery solved.
Yeah, if you just allow this, just so before we
Mhm.
continue, so we have everything at the right place.
Okay.
Because I think this is the one that you mentioned at the beginning you were not clear about.
Yes.
So
that's
if we have that, then we
that's
should
the
be,
one step. Yeah.
Okay. So this thing is the definition of a four-dimensional sphere. Just plug this in. Maybe you can already see that a couple of these angles are just going to drop out because you get a lot of sine squares and cosine squares, and as you know, these add up to 1. So there are a couple of these angles that are going to drop out, and what you will end up with is exactly this relation.
Interesting.
So at the moment that Nelson wrote the definition, and he wrote to parameterize it, this was a choice. He chose to parameterize it in this way, then this is the automatic mathematical result. There's no new input there.
Okay.
So back to the original story, just to combine everything. And so if you allow me just a small summary, because there's good maths here, and just to put it in physical perspective.
Yep.
Does everybody understand why this is the starting point? There's two things to understand here. One of them is that there's a minus sign. You alluded to it. You said, well, the minus sign, I guess it's definition or something. And you said this for general Robertson-Walker metrics. Is that clear why it should be this? There are two questions here. Why the minus sign? That's one. And secondly, why is this the general for Robertson-Walker metrics?
Well, the minus sign probably comes from the ds squared being defined as minus d tau squared.
Yes,
Mm-hmm.
that's correct. There's some c's missing.
Yeah.
C equals on units, sure.
Yeah.
Okay.
You just multiply those out and you would get the normal line elements.
Yes. And from the very first lecture, I told you that one thing that all relativistic line elements have in common, that there's always a minus sign between the spatial and the temporal parts. Where you put the minus sign is author and lecturer dependent. In the ds squared, it's typically put over here, but the fact that you have a minus sign here and not here is a general requirement of general relativity. The shortest reason I can give is that all curved space-time, so including this one, should at the very least have special relativity built in. And as you remember from the first lecture, you can only get special relativity at the moment that there's a relative minus sign between space and time. Without it, if both would have plus or both would have minus, you would not get special. You would get some other strange theory of nature, but not special relativity. So that's where the minus sign comes from. And this part, the Robertson-Walker part, why is this necessary for Robertson-Walker?
So the a squared is just something you take out, right? Because every single spatial.
This one here, you mean?
Yeah, because every single spatial component has the a squared in there, so you can take that out.
But now you're sort of
Yeah, okay.
you assume that this is true. Yeah, then the a should be there to
if
get this. But suppose that you didn't know this. Okay, this is secret.
Can I show something as well? This is basically a temporal part of your space-time metric. This would be a spatial part of your metric, right?
Yes.
There is the thing we talked about with isotropy and homogeneity, I think, that at any given time, the universe will look homogenic and isotropic.
Yes.
But, well, basically, like, spatially it is homogenic and isotropic, but it's not so temporally. And this a squared times t term basically describes how this isotropy or homogeneity changes in time. No? So like you have your spatial part of your metric, and it does change over time.
Agreed. It's the right ingredients. I'm not too sure about the formulation, but I think that the physics, the intention of the physics is correct.
Mm-hmm.
You remember the cosmological principle? The universe, exactly as he's saying, the universe looks the same, or by the same I mean in every direction you will see the same thing, and this is true at every position in space. Everywhere you stand, you can look around 360 degrees and get the same picture. But that means that the spatial part has to have a certain form. And he calls it dl squared here, and then he specifies could only be three of options, right? Could flat, spherical, hyperbolic. But the cosmological principle, this idea that the universe should look the same in all directions as seen from every position, doesn't necessarily have to be true at all moments in time.
Yes.
It doesn't have to look the same in time. So that means that this part, if you assume for some reason that this is space, that this is homogeneous and isotropic, then this still is. It's just at every moment in time it will look different.
Yeah.
But at any moment in space it will still look different.
Yeah, that is what I was going for.
Yeah, I know. I got that from your words. So yes, this really is the most general form of your Robertson metric that you can put in, under the condition that this thing is the dl squared is itself spatially homogeneous and isotropic. That's all there is to it. And then he goes on to specify, well, what is dl squared? And then he said, well, for spherical space it would look something like this, work out the math, and indeed he will find ultimately that, first of all, you get this line element written out with this additional angle because you're now in 4 dimensions, 4 spatial dimensions. But then he says, no, but I can write this redundant 4th dimension. I can write it back into one of the actual dimensions, namely distance. Because that's what you do, right?
Yeah.
At the moment that you have a 4-dimensional space, then you know that at least one of the components, one of the coordinates, is redundant. Should be a rewrite of the other coordinates, because we know we live in a 3-dimensional space, so the 4th-dimensional thing could only be a mathematical construct built up from the other 3. And that's what he does here. He says, well, I have my 4 coordinates here, but they are related to each other in this way, in a spherical way, so I should be able to eliminate one of these coordinates. Then he does the math, then he finds this.
Yes.
But it also means he now knows how to write psi, this redundant coordinate, in terms of one of the non-redundant coordinates. He's also able to write deep psi into dr. And when he does that, following the math,
here.
then he gets this, which is indeed exactly a spherical universe if you assume k is positive. This is your series of steps.
Yes.
Okay.
And there's like a little bit more. I also like figured out at home how to show that like k basically has to be in the metric over there. You can do the same type of derivation for the flat and hyperbolic scenarios, like I said. Can I erase some of this here?
Sure.
Okay, I'll just write this.
It's good to hear here.
I'll just copy the result of it back onto the board. You can do the same type of derivation for example, a flat scenario where r, as I said, is equal to just the angle itself. And if you then try to calculate what deep psi squared is, what you'll get is deep psi squared is d r squared, and this doesn't really resemble this over here yet, but there's a really simple thing you can just say about this that I'll explain why I did this later on. Write it like this. If you would then have a k factor of 0, which is what the k factor is for a flat universe, this r would be multiplied, or r squared would be multiplied by k. It would just end up with only 1 in your denominator, which is what this is. Right? Is that clear? And then for hyperbolic, the same argument goes that you have r is sine hyperbolic psi, then is equal to cos hyperbolic psi d psi this one here. And with this hyperbolic cosine squared, you can play a similar game as we did with the cosine square we had in the spherical derivation. There's another trigonomic identity here that is a little bit different than it would be for, let's say, regular non-hyperbolic cosines and sines and such, which is that the hyperbolic cosine squared is equal to 1 plus sine sine h squared of psi. We define sine h square of psi to be r, so then we get dr squared minus 1 No, plus, of course, r squared. If you would take your k factor as -1, as it would have to be for a hyperbolic universe, you have minus times -1 here, it's just a plus, so then you get this form as you basically got over there. So this notation of using k basically just makes the metric general for all three types of universe that we can have for those spherical, flats, and hyperbolic ones. Because you find a result for deep psi squared, all have the same form, only that you would have your r squared multiplied by a different term. You could also just write it as, for example, 0 times r squared, or write this one as dr squared, or minus r squared. This minus there, the 0 there, and the 1 that is in front of here would then correspond to the k factors.
Okay.
Questions?
Yeah, I don't know if I'm just gonna say something really stupid, but so you introduced a new coordinate, it's psi.
Yes.
It's the one you've used to determine what the values for the metric are. You know what I mean? Like you got the psi squared.
Oh yeah.
And those are the values that you write for your metric.
You mean this here right now?
No, the geodesic. No, not the geodesic. Oh, I forgot the name. The one
Line
at the upper left.
Line element.
No, upper left.
Metric.
Yeah, the metric.
Okay. Okay, fine. Yeah.
The values on the metric, you got those from the psi squared.
Mm-hmm.
And I was thinking that, well, the metric tells you how curved the space-time is, which is, could you say that it's like a four-dimensional way to view it?
Sure. Yeah.
And you got that from your fourth-dimensional coordinate, so I was just thinking, is that just coincidence, or is it?
I don't think the four-dimensionality of that one is per se related to the four-dimensionality of this, because in this case you have 4 spatial dimensions, and here you have 3 spatial dimensions and 1 temporal dimension. So the four-dimensionality of this one is not related to that of this one.
That's true.
Because as we've seen, thanks to Gideon, this 4th dimension we introduce here, we can reduce to one of the dimensions we already had through this working out of all of this into this and getting that.
So the fact that you use this psi squared to get your values for the metric, is that because the book told you to do so? Or
This is one way of doing such. There's several different ways of going about this. I also found one online that I looked at that doesn't use I think it does use 4-dimensional spheres, but not exactly in the way they do here. There was a different type of derivation.
It's all the correct answer. So I'm going to say the exact same thing, just maybe slightly in different words. Yes, the metric is 4-dimensional. It says something about the curvature of 4-dimensional space-time, including time. Now, the cosmological principle requires us to have the spatial part of the 4-dimensional space-time to be isotropic and homogeneous. But we know that space itself is 3-dimensional. Now, one way to describe curvature in a 3-dimensional space is going to a hypothetical 4-dimensional space, not 4-dimensional space-time. You take your 3-dimensional space, you introduce a non-existent mathematical construct. Well, the mathematical construct exists, but it doesn't exist in physics. You take this 4th-dimensional space and look at this 3-dimensional thing from this 4-dimensional space.
Mm-hmm.
Now, you know that this 4th dimension that you've introduced is redundant because it really doesn't exist. And that means that this 4th dimension that Nelson originally called W should be related to the ones that do exist, X, Y, and Z.
So mathematically speaking, would it just be linearly dependent on the other dimensions?
Not linearly dependent per se, but here's a relationship. And that's exactly the one that he derived there. Exactly, that's the one. He says, if you go through the math, you will find this 4th dimension that he introduced, this W, or equivalently this psi angle, is really just a rewrite of one of the dimensions that does exist, namely radius. If you take the sign of this 4th-dimensional spatial component called psi, you will get back r. So there is a difference between actual 4-dimensional space-time all 4 dimensions that really do measurably exist. And the 4th dimension that he introduces here, first of all, it exists only in space, and secondly, this 4th dimension is completely hypothetical.
And in the end, turns out to be rewritable into a 3rd dimension,
Yes.
or one of the 3 original dimensions.
Exactly. So what Nelson ends up with at the moment that he's seen how this hypothetical mathematical 4th spatial dimension is related to one of the other 3 dimensions, he puts this back into his equations, and he gets he gets done with all this 4th dimension. His final expression contains none of the hypothetical construct of this spatial 4 dimension. He gets back everything in real physical 3-dimensional space.
The only variables that are left in here, if you would plug this one, or that one back in, would just be r, theta, and phi.
Yes.
The psi would turn up nowhere anymore in here.
Yes. But you already know this, by the way. If you allow me to give you an example of how this works, just not from relativity, but just from curved spaces. There's at least 2 ways that you can describe that the Earth is a globe. Yes? One we've already discussed. You take 2 people, you let them start at the equator, and you let them walk upward. At some point they will meet. And that's because the globe itself has this shape. It's nothing to do with the walking of the people. It's because the thing on which they are walking is itself curved. This is a way to find out that you live on a curved space. Take 2 people, let them walk in a straight line, and if without them changing direction, they still end up finding each other, this means that you're on a curved space. Right? This is an inherent way of checking that you're on a curved space. There's another way of checking that the Earth is round. Namely, you go 1 dimension up. In our case, we'll be literally taking a rocket and blasting away from the sphere and looking back. And then see, oh wait a minute, the thing on which we lived is really a globe. That's what he does here. He says, well, let's suppose that you have a 3-dimensional space, this thing. Let's suppose that you can blast away from that thing in a hypothetical dimension that he calls W, and then looks back and sees how that thing looks. And then he says, well, it looks like this. So the difference between my globe and blasting away and looking back is that in our case, you can actually blast away. That 3rd dimension really exists. Here it does not. But you can still do the maths. So there's 2 ways of finding curvature. One is inherently, not blasting away, staying in your 3 dimensions and just looking what geodesics do. If they curve towards each other, you're in curved space. Or you blast away in a 4th dimension that doesn't exist. By this mathematical constant, you blast away in your rocket, go in that dimension, look back, look at how curved the thing is, and then reduce everything back to your 3 dimensions. That's the second part is how he did it here. Here he took his 4th dimension. Here he blasted away, found that it was curved, and then rewrote everything back into the 3 dimensions. That's how he did it.
So could you do the exact same thing by just looking at a 4D surface and a 5D
You could, yes.
superspace?
Yes.
If you really would.
Suppose that you find yourself in some branch of theoretical physics where somebody has decided, you know what, space is 4-dimensional. Really,
Yes.
physically
Yes.
4-dimensional. And you want to know how curved that space is, you can
just do the same trick.
And blast away in your 5th dimension.
Yep.
Is it for me or for?
No, for you.
Okay.
Is that why in string theory they introduce all these extra dimensions, so that you can give a mathematical description of the spatial mechanics of an x dimension if you don't analyze it from an x plus 1?
No, in string theory they you know this, right? String theory says it has multiple spatial dimensions, 1 time dimension, multiple spatial dimensions. It's really just this thing again. Where is it? This thing, but now with more terms than the dl squared. But all of those are physical. They say it's not hypothetical mathematical constructs. These are actually existing spatial dimensions. And of course, then these people have to find a reason why you cannot measure these 7 or so extra spatial dimensions. And the way that they do it is by saying, well, maybe it just so happens that you cannot move infinitely far in those directions. Right? So maybe you can only move a ridiculously small amount of those directions, so small that you cannot notice that you're actually moving in that direction. And then it's a big problem in string theory that in how many ways can you make these 7 dimensions smaller in such a way that you cannot see them, and the 3 remaining dimensions look like our actual universe. And you find that there's 10 to the power 500 possibilities for this.
Oof.
Yeah. Well, that was the original number, and I just happened to share an office at some point when I was a PhD student with a guy who did string theory, and his research showed that it was not that bad. It was only 10 to the power 200. That was actual publication. But it turns out that the laws of physics are different in each of these. So it means that you have 10 to the power 200 different laws of physics. They all come out with a universe of 3 dimensions and 1 time dimension. It's just that the laws of physics look different. And then the discussion started, are we still doing physics now? Because we have 10 to the power 200 different predictions. And then you do an experiment, you say, look, it fits. Well, yeah, sure. I mean, if you make 10 to the power 200 predictions, and I'm sure one of them will fit, yes. And there was an actual philosophical discussion on whether you are now still doing physics. It's like going to your to a sightseer, right? A lady with a crystal ball and a circus tent. You go in there and she says, well, I have a prediction for you. Next week on Tuesday you'll meet the love of your life. But then again, it might also be Wednesday, it might also be Thursday, it might also be next year, it might also be 2 years ago. It might also not happen. At some point you say, look, I met the love of my life. Would you say that that lady has predicted the future, has done a good prediction? And I would say the answer is no. If you make ridiculously many predictions, then sure, one of them is bound to be right. So this is see what they do in string theory. Actual physical extra dimensions. Try to see how you can fold them up in such a way that you can only see 3 of them and the other 7 are so small that you cannot see them. But again, folding them up in a certain way gives you a different set of universal laws, and then you come up with 10 to the power 200 predictions for how the universe should look. So yes, one of them fits. Oh yeah, this is the derivation, by the way. This is one of the ways that you can derive the Robertson-Walker metric.
Everybody happy with it?
Yeah. Any questions, Laura?
Cool.
Now, for the people who would like to read this in a somewhat different way, but very similar, I wrote these series of lecture notes a long time ago in cosmology, and I put it on Aleum this morning. And it also includes another way of deriving this thing. So you can look at this one, you can also look at the one on Aleum, but in both cases you should be fine. I think this is very clear.
Okay, great.
Yeah. All right. So should we do an applause? I think Okay, great. Now, this is a very nice warm-up because we have some exercises on cosmology right now. If you recall, one of the exercises that I gave was, now given that you know this metric, this Robertson-Walker metric, in the most general case, what are a basic exercise? What are the Christoffel symbols? What are the geodesic equations? How do things move in such a space-time? That was exercise 1 of the homework set. So I would like to go through that. Only part because most of this exercise is really just standard material that you should be able to do right now. It's just given a metric, calculate Christoffel symbols. So I would like to do 1 or 2 of them just to show you how it works. Write down the geodesics and see if we can make sense of it. After that, there are some exercises on, given that you have a space filled with a fluid, right? This gas, if you will, of particles or energy, and you have this metric, how will that universe evolve in time? How will A, the scale factor, get bigger or smaller? We've already done one of these exercises. Last week on Monday, we did it for a curved space-time, Robertson-Walker space-time, in which there was matter. And we found, oh look, that thing expands, but the expansion slows down. That's what we found. Let's do the same exercise for a radiation-filled one and our big friend, the dark energy, just to see what happens. So I propose, if you will allow me, just to write down the Christoffels for this one. Yeah, and then we go on with the break, and then we'll see if we can make some sense out of the geodesic equations. Now, it's a good thing that we already have the metric. Because we can plug it immediately into our definition of the Christoffel symbol. I think Lizzie last time asked me if you should know this by heart, this definition. No, you do not. You will get a formula sheet from me. Do correct me if I'm making mistakes, because I'm doing it from memory right now. You would think that at some point I know this by heart, and I think I do. There you go. There's the definition of the Christoffel. Yes?
I'm not sure, but is it on the minus missing at the beginning?
No, this is fine. You mean in the definition of the Christoffel symbol?
Yeah.
No, this is the way that it is. Okay, there we go. Here's our metric. We have a number of Christoffel symbols. I found about 12 or so that are non-zero.
It goes 13.
13? Let me just count how many I had. I think it was 12-ish, but maybe it's for 13. Let's check. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 13. I got 13. That is not to say that we have the same answers, but we've passed the first test. So which one shall we do? I mean, we cannot do all 13. Takes forever. Let's do 1, 2, maybe 3. If no preference, I'm just going to randomly pick. Let's start with the, which ones are the most fun? Yeah, sure, why not? Let's do the R Christoffels. The Christoffel symbols as they appear in the geodesic equation for the R coordinate. So this is for the case that mu equals the R coordinates. At this point, I guess everybody is certain what to pick for nu here, yes? Pick it R as well? Why is that? Just checking.
Because otherwise, even that term is going to be 0, right? Because it's
Yes,
a diagonal matrix.
exactly. In the fortunate circumstances, and this is not general, but in our cases it sort of is, our exercise is going to have diagonal matrices, where in the happy circumstance there's a diagonal matrix, so that means that the only non-zero ones are on the diagonal, and that means that this one has to equal that one, otherwise it will be 0. So that means that there's a contraction of nu with these here, but the only ones that survive is when nu itself is also R. So immediately I can write down RR. Sound like a pirate when I say that. So beta. Yeah, let it sink in for a second. I thought it was funny. Yeah. There you go. Oh, here, mistake. Let's see, this is a beta, this is an alpha, this is an R. Okay. So it should be this. So this is just me applying the fact that it's a diagonal matrix. So when mu is R, then nu should be R. And let's identify these three terms. When are these non-zero is the question. How about this? When is this non-zero?
When R and beta are equal.
When R and beta are equal. Yes, well that is of course very true. Again, it's a diagonal matrix, so this only is non-zero itself, this metric element, at the moment that beta itself is R. So this is only non-zero if beta is R. So that means we're here. This is a GRR.
And alpha would have to be either t or r as well?
Yes.
Because you can only take t and r derivatives.
Exactly. This thing depends only on time and on the radius itself, so that means
Wait,
the
why
only...
is that one R? Isn't the first, that's the second one.
You're right.
That's theta, right?
Yes, you're right. Excuse me.
Oh,
It's
same
one.
argument.
Yeah, this is theta. I'm
Yeah.
sorry, but the conclusion still stands, right? The only derivative you can take of this thing is either a time derivative or a radial derivative. So that means that the only possibilities here are when alpha is either R itself or this t, and in all other cases, this thing is going to be 0. Here, same thing, but just with alpha and beta reversed. Again, the only way that this thing itself is not 0 is when alpha is R. So you get GRR again, which is this one. And the only derivatives that work on this one is when beta is T or R. So those are the only options. How about this one? When is this non-zero?
When alpha and beta are equal and the metric entry has an r in it?
Yes. First of all, alpha and beta have to be equal because, again, it's a diagonal matrix. And it can only be the alpha and beta such that it has an R dependence in that metric element because we're taking an R derivative. So this one works, has an R, this one has an R, that one has an R. So that means alpha has to be equal to beta as long as they do not equal the time component. because this is the only one that is not R dependent. So really we've laid out all the options here. And now it's just a matter of putting in the functions. So here's one. We saw that if alpha is R and beta is R, right, that's this option, then, well, all alphas and betas are just R, right? I get this. All of these are GRRs, and you take the derivative with respect to R, so it's 3 times the same thing. 2 times plus, 1 times minus gives you 1 times plus. And now you just put in the numbers. GRR with the R's upstairs. Just checking if you know what that thing is. Yes, it's the inverse. And again, it's because it's diagonal matrix. Otherwise, the inverse doesn't look as simple. Right? The GR. Sorry?
If it's not diagonal.
If it's not diagonal, then the G with the indices upstairs is not 1 over this one.
Yeah, but how does it work?
Okay, here, there you go. That's the rule.
Is that a Dirac delta?
It's not a Dirac delta, it's a Kronecker delta. It's the discrete version of the Dirac delta. The Dirac delta, for the people who've done electrodynamics, means it will only give you something at the moment that that the thing inside is 0. Or, if you will, a Dirac delta, x minus y, will only give you non-zero if x equals y. This is a Kronecker delta. It has the same rule. Alpha and mu have to be the same, otherwise the thing will give you 0.
What's the difference then?
This is discrete, because you can give x and y any number that you want. And this is, this is continuous. X and y can have any number that you want. This one is not continuous. It has 4 distinct values with nothing in between. So this is the rule how to do this. And this is an algebraic equation in 10 components, because you're looking for 10 different components of your metric. So this is a huge set of 10 algebraically related equations that you have to solve. And unfortunately, it's difficult. By the way, do you notice that this thing, if you write it as a matrix, is just the unit matrix? Because at the moment, right, this is the row, this is the column. At the moment that the row and column are not the same, it will give you 0. And at the moment that they are the same, it will give you 1. 1, 1, 1, 1. This thing is the tensor version of the unit matrix. Anyway, long answer to a short question. Generally, you would look for your inverse metric using this rule, solving this equation, which is unfortunately difficult. In our case, it's simple, diagonal matrix. Then the inverse metric is just the inverse of the terms. So we can apply that here. GRR, that means the inverse of this thing, which is 1 minus kr squared divided by a squared. And then we have to take the r derivative of the non-inverse thing. And this, of course, you can easily just work out, right, what the answer is. What I get is this, kr over 1 minus kr squared. Maybe you can already see why that is. There's no fancy mathematics, it's just taking a derivative. First of all, these a's will drop out, right, because they're not r dependent, so they're just constants, so this one cancels against that one. If you take a derivative of this thing, you will get 1 over the denominator squared, right, because the derivative of a fraction. 1 over the denominator squared cancels one of the numerators here, leaves you with only 1 here, and then you have to take the derivative by the chain rule what is in here, and that cancels this 1/2 because of the r squared, and you get this out. So there you go. That's one of them. That's this one. Oh, the RR one. Let's do one more. One other option that works is when beta is r, and alpha is time. This one. Let's see what we have here. Alpha should be time derivative of GRR plus, well, an R derivative of GTR. This is 0 because TR metric element is 0 itself, minus the R derivative again of TR. Oh, look, it's our good friend super 0 again. You see that? Because this thing itself is 0. Its derivative is 0. And even if it were not 0, then they would cancel each other out. So it's triple 0 or something like that. It's ultra 0. I don't know. Yeah. So these things you don't have to worry about. And you get something like this. And now it's just a matter of putting in the metric components and see what happens. 1/2 GRR. The inverse of that thing, so that is 1 minus kr squared over a squared, then take the time derivative of the thing, which is a squared 1 minus kr squared, and this is easy, yes? First of all, this is t independent, this is t independent, so the derivative does not feel this thing. It just goes out of the derivative here, cancels this one, so you don't have to worry about 1 minus kr squared. 1 over a squared, then you take the derivative of a squared, gives you 2 times a times the derivative of a, right, chain rule. 2's drop out, this drops out, I get a dot over a. And if you recall from last week, we also call that thing the Hubble constant. It's the expansion of the universe divided by how big it is now. That's what it says. And now we have another Christoffel symbol. Now, you can go through the whole list. Right, there was more options here. The alpha and betas, if there are the thetas and the phis, it also gives you a list of options. It's just the same exercise over and over again. So I propose to do the following. Let's have a break. In the meantime, I will write down all the Christoffels and we'll continue from there after the break. Any questions so far? No? You a question maybe? No? Okay. How's your physics?
Well, not that good, but
Okay.
I get the math part of it.
Do you have a mathematical background?
No, just from high school.
Okay. Oh. We should introduce this in high school. Apparently, it's, I mean, no issues there. Okay, great. Okay, we convene in 10-15 minutes or so. In the meantime, I'll write down Christoffels. Second part of the mixed bag is just do some more exercises on cosmology. Before the break, we went through calculating 2 or so of these Christoffel symbols. If you go through the whole list, this is all of them. No mathematical and or physical difficulty here, just going through the math, and this is what you find. They look beautiful as they always do, just as the geodesic equations that come from this. This is exercise C, yes, that you write down the geodesic equations. That should be no problem for you, yes? Just to be sure, this is what you do. We made a whole point out of proving that the path through space-time that takes the least proper time is this equation. Double contraction, an alpha and a beta, and if you then plug in the Christoffel symbols, this is what you will get out. Just as a check, so let's look at this one. I'm looking at the theta differential equation here, yes? So mu is theta, so I'm only looking at my Christoffels with a theta upstairs, which are these. And I'm missing one. Yeah, there. These 3. This one, that one, that one. Note that Christoffel theta t theta is h. Shorthand notation for scale factor, the derivative divided by scale factor itself. H. Yet I write 2 times h here. Just question out of checking. Do you know why the 2 is there?
Because the Christoffels are symmetric.
Yes. Because if you do this contraction, At some point you will have the combination alpha as t and beta as theta, which will give you 1h. But somewhere else in this same contraction you will have this alpha is theta and beta is t, but that's the same Christoffel symbol, that's one more h. They add up, give you 2 times an h. As a rule of thumb, every time that you have a Christoffel symbol with the two indices different from each other, you might want to add a factor of 2 when you write down the geodesics. So this is what you get, and don't they look beautiful as they always do?
They do.
Yeah. The thing is you have to solve these things, yes? So there we go again. Man, I love how simple things were in Newton's mechanics, where this was 0, that was 0, that was 0, and that was 0. Well, that's not completely true because I'm in spherical coordinates now, but things will just move in straight lines. There might be straight lines in here, not very clear. So let's go through this. Let's see if we can make some sense out of this. This is all of this is exercise 1. First of all, these 4 equations tell you how your time, how your radial distance, how your theta, and how your phi change in proper time as a function of proper time. So in principle you can solve these 4 equations, and as always they're coupled, so that means if you say want to know how things move in the radial coordinate in the Robertson-Walker metric space-time, then at the very least you will need how it moves in theta direction. But in order to know how things move in theta direction, you have to solve this equation, which requires how it moves in r direction. So they're coupled. You cannot solve them independently, you have to solve them all at once. This is exactly, of course, what makes it difficult, and the fact that they're nonlinear. So this is the part that you don't want to tell at middelbare school, high school. Okay? It's mathematically too difficult. But there is some help. One of them is that we know one more thing about any motion in a curved space-time. Something that I've emphasized over and over again. Once you have the geodesic equations, you can solve them, but there's still one extra condition that you have to put on the motion that comes out. Do you remember what that was?
About the 4 velocities?
Yes. The Vor velocity has to be normalized, which is an expensive word for saying that this should hold in any curved space-time. Now let's just write down what this would mean in our particular case. This thing, written for our space-time metric, I've erased it, but we should be able to write this down. What else? This is just, the lower equation is just really this contraction written out for our particular metric. Right, just as a reminder, the shortest path through space-time are these equations. The path that takes you the least proper time. This is how things move in a gravitational field, in a curved space-time. But once you have found the solution, you must still let it obey this equation, the normalization of Vor velocity, because all motion in space-time have to follow that equation as well. So you really have 5 equations. But that's good news, because these 4 equations are coupled. There are 4 coordinates that you have to solve for t, r, theta, and phi. Very difficult, but fortunately there's a 5th equation that allows you to rewrite some of your missing coordinates in terms of something else. That's what the 5th one does. So usually this one comes as a happy help. Still looks very difficult. The first thing that we're going to do is check which observer is the one who measures r and which observer is the one who measures t. I hope you remember this from the lecture on black holes, that once somebody has given you a metric in terms of coordinates, then you have to first identify which observer it is that measures these coordinates. Sometimes there's no observer that does that, and really just mathematical bookkeeping devices. And before you can do any physics, you have to identify, well, who is the person who measures r? It looks like a radial distance, but who is the person that if he would lay his ruler against the radial direction would actually measure that number that comes out of r? Who is that person? Who's the person who measures between two exploding firecrackers how much time there is? Whose t is this? Because one person's time is not the other person's time. So before we continue, we have to identify r and t. Suggestions. Who is the person who measures r, this r, and who's the person who measures t, if anyone? Maybe it's none. Maybe it's a mathematical bookkeeping device. If you don't know the answer, at least try to think of a way to find this out.
We can do what we did for the Schwarzschild metric, okay, in the sense that for dt we checked if there's anyone for whom dt is equal to d tau.
Yes, that sounds like a good idea. Okay, that's great. Because d tau, if you recall, right now one more equation. By the way, if it's okay with you, I'm really going to drop the c's from now on. I mean, they're driving me crazy, especially when I do my own equations, right? Because as you know, I use c is 1 always in any calculation. So every time that I try to write down something for you, I have to put the c's back in, and somewhere midway the calculation I forget about it. And so right now I'm just going to forget about them. So there you go. Here's our line element. I really should not have just erased Nelson's, because I think he already had everything written down. Squared minus r squared t r squared sine theta squared d phi squared. I think this is it. Yeah, that's it.
Yeah, that should be it.
Yeah, that's the line element for Robertson-Walker metric. Yeah, you know that this is always the amount of time between two events for any random observer, and which observer it is, you have to find out by plugging in his r and theta positions and such, yes? Now Nelson just suggested that maybe what we can do, if we want to know who dt is, we have to find that one observer for whom dt is d tau. D tau is the amount of time actually measured by an observer. If we find who that person is for whom d tau is dt, then we know that who dt is, who is the dt measurer. So really the question is, how do we get rid of this? How do we make that 0? The observer for whom this is all 0, the spatial parts, is the one for whom d tau is dt. In other words, that person is the one that measures dt as his time. Now who is that person?
Well, it's not dependent on r, who the person is, right? If that whole spatial part there is equal to 0, then all you're left with is d tau squared and dt squared.
No, that's not true, is it? No, it's a good suggestion. One way to get rid of these two at least is say, well, let's take the observer who's in the center. R is 0. Because then all of this is 0. And this will be a squared times dr squared. Which is close. But this also has to be 0 in order for dt to be d tau. So we have a conclusion now. It's not the guy at the center of this coordinate system.
Infinitely far away? Also, no, actually, no.
So what happens if you take infinitely far away?
No, because then the first part can be 0. No,
Yeah.
the second part can be
Yeah, that sucks.
infinity squared.
Okay, so it's also not the guy who's infinitely far away. It's an important question. It's not just mathematical teasing. This is really, you have to identify who this person is in order to do any physics. Right? Otherwise you calculate numbers, but you have no idea whose distance or whose time it is. There's a very simple option, by the way, to make everything 0, like except for the dt part.
A0.
Oh, A0. Oh, yeah, that works. That's good. Yeah, you're right. I wasn't going for that, but let's take A0. What does that mean?
The universe is not expanding.
No. A dot is 0 means the universe is not expanding. A dot is the A is the distance between 2 points.
True.
And A dot is how this distance is growing or not.
Is it like the universe is one infinitesimally small point?
Yes,
Mm-hmm.
because you say that all points are squeezed, all points are at a0 distance from each other. But you're right, we would get that. So, no, really, it's correct. I mean, dt, or dt apparently is the amount of time that has gone on for the person who was there at the center of the universe when the Big Bang happened. That's his time.
Nice.
Oh, it's correct. It's beautiful.
Yeah, that's pretty cool.
Note that later on, any moment later on, this does not hold anymore. Right? Because the observer who was at the center of the universe, whatever that may mean in this particular context, doesn't exist anymore. Because A is not 0 anymore. But in principle, what you can say is, well, there was an observer once at the beginning of the universe, that guy in the center of the Big Bang, his time is dt. And then later on, maybe that guy doesn't exist anymore. I'm not talking that he exploded because the Big Bang and such, but simply because the conditions for A to be 0 don't exist anymore. But you can mathematically say, well, the hypothetical guy that was there at the beginning of the universe, God, if you will, or something like that, that guy, that's his time. So it's correct. Yeah, that's nice. I wasn't going for it, but sure. Yes?
You also say like if A is 0,
Yes.
that dt like is measured by someone who's like infinitely far away, because like if you're like far away, then you see like also like difference between 2 points really
And A
small,
is-
like you know what I mean?
Yes,
Like,
yeah,
if I see someone,
yes.
Close to black hole, but I'm infinitely far away, then I see this as one dot.
Well, that is very true, but we have to be very careful here. It is a very good suggestion. Louis is saying something like this. I mean, freely translating what you're saying. The distance between you now is what, 40 centimeters or so, right? So if I would take your distance here, it's not actually 40 centimeters. For me, it's like, I don't know, 7 or so, right? And if we get closer by, say, oh, wait a minute, it's really 40 or whatever it is. So the further away from each other, the closer you appear to be with respect to each other. Okay, the keyword here is appear. You are really just 40 centimeters apart from each other. What you're talking about is if you're going far away, then things look closer to each other as an optical effect. They are not actually closer to each other, not even for me. Because if I do a measurement, that means that I look at the ruler that is over there. And I look at the numbers on that ruler. The ruler might look smaller, the numbers are still the same. So you're right, if you go far away from something, oh sorry, oh that's a chair, I thought it was your leg. If you go far away from something, I think you have long legs and stuff.
Not that long.
No, apparently not. If you go far away from something, then things look closer to each other, but the numbers are not really different. Not even for the guy who is far away. So that's just an optical effect.
Parallax, right?
Yes, you would call that parallax. Yes, especially if you would move, so the difference would change a little bit. But you're right. Yeah, forget who said it. Who came with the suggestion? A0. Oh, Andreas. Okay. So yeah, that actually works. We might actually just call it God time from now on. The guy who was there at the beginning of the universe, or something like that. Okay. There's another way of getting there, of getting the same amount of time out. It's much more simple. I mean, we've been now focusing trying to get these coefficients to be 0. What if you make the differential 0?
Someone who's not moving.
Yeah. So just some guy who's not moving, right? Just some guy who sees the two events happen in this Robertson-Walker space-time at the same time. Now, who is that guy? I mean, is the guy standing over here, the guy standing over there? That doesn't matter. Because any person, no matter what his r or theta position is in the space-time, at the moment that he's not moving, he sees the two things happen for him at the same time, then this is automatically 0 for all of them.
He's not moving in respect to what?
To the space-time.
Do you mean like happening at the same time or at the same place?
Excuse me, same place.
Okay.
Yes, I misspoke. I'm sorry. At the same place. And that could be anywhere in the space-time. And then the question is, well, moving with respect to what? With respect to the space-time.
So just fixed location.
Yes. This person has a very special name. When you came up with the A0 person, I called it God time. Just made it up now. But here's an actual name. The guy who is not moving with respect to the space-time is called the co-moving observer. And there's a subtlety there, and I have to be very clear about that. I say co-moving. By co-moving, I mean that he's not moving. Now, that doesn't make sense, right? terminology
With
wise.
respect to what?
Is it with respect to the universe?
With respect to the universe, he's not moving. He's standing still within the universe. Here's the subtlety. Does that mean that the guy is not visibly moving? The answer is no. He is actually moving. But we have to be sure if you see why that is. There's a subtle but very important, very physical distinction. It's not just terminology. There's physics there. In order to do so, let's move to a related but separate question, and I will tie everything together. What is the distance between any 2 points as measured by a random guy? So I want to know, there's 2 firecrackers exploding in the space-time. Let's make it more universe-like, cosmology-like. We have 2 supernova going off or something like that. And you want to know what the physical distance is between the 2 supernova. So I want to have delta S, the distance between the 2 exploding supernova. How do you calculate that generally in general relativity? How do you do this? We did this in a tutorial a couple of weeks ago. We're not in the Minkowski space-time anymore, so it's not the Minkowski line element.
Space-time interval.
Yes, we need the space-time interval. That's this one, isn't it? But this one is the one that tells you something about what the amount of time is in between 2 things. Do you agree with this? Do you remember how you can switch this to how much space there is in between 2 points? How do you do this?
Well, it has spatial and time components.
Yes.
Time C.
There is a C involved somewhere, but I put it to unity. If you want, we can put a C in there somewhere, but sure. Okay, let's put a C. Let's be clear, it's a C squared. You remember this?
Yeah, then we needed to integrate over the entire proper
Yes.
things.
And we will do so in a second. Just generally speaking, not just Robertson-Walker spacetimes, any curved spacetime, the idea is the line element written as d tau equals such and such gives you the amount of time in between 2 events. If you make this switch, you replace d tau by ds, and yes, that includes a minus sign and c squared, you will get the amount of space in between 2 events. So anytime somebody asks you, well, calculate for me what the amount of space is in between 2 events, switch to ds. What does switching to ds mean? Well, add a c squared and a minus. So let's write that down for a second. And again, I'm putting the c's to unity again. Here I made that switch. Now my question was, if I tell you that 2 firecrackers have exploded, or supernovas have exploded somewhere in the universe, and I want you to tell me what the distance is between those 2 exploding supernovae as seen by you. I'm asking for this number. What is the very first thing that you do when you want to calculate a distance between 2 things?
Make sure you measure everything at the same time.
Yes, exactly. Because maybe the supernova were moving or something with respect to each other, something like that, right? Okay. So that means that by definition, if you want to turn this into the amount of distance that you see, then you set this to 0, because there's no point in measuring the one position and the other position if things are moving with respect to each other. You have to do this at the same time, otherwise you get a different number out. You get a number out, but not the number that you're looking for. So just the fact that we're looking at something, we're looking at an actual distance, requires us to set this to 0. Now what I'm going to do next is I'm going to say, you know what? I'm going to assume that these 2 things, these 2 supernovae, happen at the same radial line from me. In other words, that I say, well, there's no distance, no difference in their angular position with respect to me. If I do that, then the distance that I measure, ds, equals a squared, 1 minus k over r squared, the r squared. Now before I continue, am I allowed to do this? Am I allowed to say, well, any two supernovae are on one line with respect to me? One radial line? But why?
Because you basically take any point in the universe as your center and just like measure radial distances from there.
That's perfect. Okay. No, that's perfect. Just his answer, rephrased. Say in a Schwarzschild space-time, black holes, you would not be allowed to do this, right? If you have a black hole over here, there, and this is the point from which you span up your space-time, and you have one supernova exploding over here and one over there. Well, here's one radial coordinate, here's the other one, and they do have a difference in angle. Agreed? And there's no way that you can turn this mathematical exercise in such a way that these are on one line. That's because there's a black hole in the middle. Not so much the actual physical effects of black holes, spaghettification and time dilation and such, simply because the black hole tells you where the middle of this space-time is. There's a fixed point in that space-time. Now suppose that you have a space-time where there's no fixed middle point, where any point is as good as the next point. Let's say a space-time that obeys the cosmological principle, say. Right? I mean, this is the cosmological principle. You should be able to do your physics with the Robertson-Walker metric from any point in space in any direction. So in a Robertson-Walker space-time, you don't have this thing. And you might as well say, you know what? There you go. There's my middle. And now they're neatly on one line. So there's no, I'm not cheating. I'm not making a special case out of this. I'm just saying, well, of all these possible points from which I could span up my space-time, or Robertson-Walker space-time, I'm taking this one. You don't have to. I mean, feel free to take this one, but it comes with a price. The mathematical price is that if this is d phi, that you cannot set this one to 0, and you have all this extra mathematical baggage that doesn't contain any physics. Okay, so the cosmological principle saves us again. And now we have the distance between the two exploding supernovae. This is for infinitely close supernovae. In order to make it actual supernovae, you have to integrate both sides, and you get this. Oh, excuse me, there should have been a square here all along. Taking the square root of both sides. There you go. What I have written down now is Hubble's law. You've heard of Hubble's law, right? Do you know what it says, just in words?
It's about redshift and blue shift, or the expansion of the universe?
It's the same phenomenon. It's the expansion of the universe, and yes, it translates phenomenologically into redshifts and blue shifts. It's the idea that any 2 points in space are moving away from each other with a certain fixed number. It's actually not fixed, it's not a constant. It's a number that itself changes in time. There should have been a squared here. In fact, you can tell what that number is, can't you? Because look, you can take the a outside. There you go. This is the amount of space that somebody would actually measure. This is the amount of space, dr, that this observer that we haven't identified yet will measure. But apparently there's a difference between what you actually measure as a person in this universe, that's this number, and what this hypothetical other guy measures, that's number. What's the difference between those two guys? Well, one of them is that there's an a in between. And the bigger the universe gets, right, in its expansion, the more distance an actual observer will see between 2 points. This is why it's called the scale factor. It scales up the universe. Now, then what is this number? Well, this number is due to the curvature, not its expansion, the curvature. Let's take the very special case of a Minkowski flat expanding spacetime, so K0. Then you would get this. Or, if you will, a times delta r. Do you see that? So, the coordinate that you have in your line element
tells you a distance in some hypothetical coordinate, and if you want to calculate what is the actual measured distance in a Minkowski flat spacetime, just multiply by the scale factor. That's what it says. That also allows us now to identify who is the guy that measures dr. It's the guy for whom ds equals dr. Now, what guy is that? Go to the general case again. This is a distance somebody measures. We're identifying who is the guy who measures dr in our line element. Well, then all of this has to be 1, agreed? Because then the physical distance agrees with the distance in a line element. Now, when is this 1?
Is there a case where it's 1 or is it not?
There is. It's a very hypothetical case, but there is.
We want the result of integration.
No, we can. That's one way we can do it a little bit faster than that. But do you see what my question here is? We were looking for the guy, the observer, for whom dr is the actual physical distance. I wrote down the general formula for the physical distance, that's this thing. I want to identify who is the guy who measures dr as his physical distance. Well, that is the guy for whom this is 1. And then the question is, which observer is that? I can tell you one thing, it's not God, the observer God. Because observer God would say A is 0, yes? And that would mean that for God everything is is at the same point. That's what you expect at the Big Bang, everything happens at the same point.
So the integral of square root 1 over 1 minus kr squared is going to be 1 over a.
Yes.
Yes. This is a good question, isn't it? But how about this? Suppose that we say, so this one does not work. Suppose that we say, well, you know what? Let's go to the Minkowski space. Minkowski expanding space, K is 0. Then we don't have to worry about this anymore. Then we're close. Then A times dr should equal ds. How can we make dr equal ds? What should A be, the scale factor? 1. Okay. Extremely hypothetical, but I warned you about this some tutorials ago, that sometimes the coordinates in which we write things are very hypothetical persons. Here's one very hypothetical person. The guy who was there, supposing that he lived in a flat space, and he did his measurement at the moment that the scale factor had the value 1, that's the guy. That's the guy who measures r as the distance between these 2 exploding supernovae. Yes. There you go. Just checking my notes if there was something else I want to add to this, because this is very hypothetical, isn't it? I mean, there's a guy, and suppose that he lived in a flat expanding space-time, and suppose that he did his measurement at the moment that things were, that the scale factor had exactly the value 1. That's the guy for whom dr is actually the measured distance. So there's that. Yeah, it's hard to envision, hard to make a picture of this, isn't it? So let me try to make this, I mean, it's correct what I'm saying, but let's see if we can make a little bit more physical intuition out of this. Let's write down our space-time as a picture. Now we've chosen some origin of my coordinate system. As we discussed before, it doesn't matter which one it is. So let's just take this point. And from this point on, we have our coordinate system. These are different r's at different angles. Right? Here's my x coordinate, Here's a phi, here's another phi, etc. For drawing purposes, not going to draw the theta direction. So let's just assume that everything happens in a theta is constant plane, just so I can draw it a little bit easier. All right. Suppose that something, here's one supernova that explodes over here. Suppose that there's not a supernova that explodes. And as we discussed, you can always put them in such a way that they are the same radial distance. Not the same radial distance, the same angles. Okay, here's supernova A, here's supernova B. Suppose that this position is r equals 1 in some coordinate system. Suppose that this one is r equals 5. Okay? That means that dr is 4. Agreed? Now I'm some random other guy, and I'm measuring what the distance is between how many meters there is in between. Is that the number 5? Excuse me, the number 4. Should be an easy question, this one.
Only if A is equal to 1.
Only if it's A is equal to 1, that's very true. At any other moment in time, when A certainly is not 1 anymore, then an observer will not measure dr between these two things to be 4. He will measure a different number. Why is that? Well, because the universe is expanding, because A is increasing in time, and that means that this distance might still be the number 4 as measured by the dr observer, but somebody who's actually doing the measurement will find a bigger number. How big is that number? Well, it depends on how big A is, how long you've waited, how much it has expanded in the meantime. Does that make more sense to you? Do you see the difference between these two things? If not, let me try one more. I did not bring it with me because I don't have one, but suppose that I have a piece of elastic plastic, and I would draw a coordinate frame. It doesn't need to be a radial one, yes, a spherical one. Let's just take a, how do you call these things? Yeah, it's just a rectangular grid, you know, with the little cubes and everything. Rijkspapier. Oh.
Cross ruler.
Yeah, I have no idea.
Or like millimeter paper.
Yeah, what you have right over there. Oh, can I have a piece, by the way?
Yeah, sure.
Okay, there we go. Here's a piece of space-time. Okay? And here's position A. I tried to put it at one of the crosses of the lines on this. And just give me a number. Not too big. How big?
3.
3. Let's make it a little bigger maybe.
6.
6, okay. 1, 2, 3, 4, 5, 6. No, it's just my marker is too thick for, the tip is too thick to have only 3 away. I've drawn the 2 points 6 of these spaces away from each other. Okay? Now I do the following. I let my space-time expand. Again, I don't have an elastic piece of this, so I would probably tear this apart if I try too hard, but suppose, right, imagine that I'm expanding this, and 2 seconds later it's about this size now. Question, how many of these crosses are still in between A and B?
6.
It would still be 6. But do you see that the actual the actual physical distance between those 2 points has become a different number?
So the unit increases.
Yes, it's the unit that it scales up.
Scales up.
It's the scale factor. That's what it does. So what is the difference between dr? That's what I really wanted to say over here, by the way, but I didn't succeed. So thank you for your piece of paper. I hope this helps. Dr is what people call the coordinate distance. The amount of spaces on the space-time itself. That if you would divide space-time up in this grid, and you put 2 points on that grid, the amount of distance in between any 2 points will not change. The amount of squares in between the 2 points will not change. It will remain 6 in our case. Even though the thing that you're measuring, that's this number, does change. That's the one.
But
Yes.
in the case of the paper, everything expands. So that's the grid gets bigger.
Yes.
So how can you measure it? Because like everything expands. You 2, your ruler 2. So that should be the same, I think.
Yes, in fact that's a question that you asked before in a different context, I think. I think it was when we were talking about spaghettification. I thought it was you, but maybe somebody else did. At some point somebody asked, well, if the universe is expanding, or in case of black holes, there's spaghettification going on, you get close to the event horizon, everything gets bigger, including your ruler. So how can you tell that you are, how can you tell the difference? In case of black holes, that was because the spaghettification is noticeable to somebody who's looking at it from far away, because it's expanding over here and not so much over there. It's very much the same here. Because if I'm going to do some ruling with my ruler is typically very short, right? I myself only take up about this amount of space. But that means that if I multiply this by A, I will only get a very small amount of expansion of myself. Yet, if I go and look at something that is very much further away from each other, for which the R is a bigger number, then A has a much bigger influence on that thing. To put that into somewhat different, more visual terms, and this is something that I've used before, I think, during one of the Brownian apertures. I used this same experiment once before. Suppose there's a difference between you and me, right? The distance. Okay? And here, let's say Francisco, so on one line here. And the amount of space, we can make it very visual. Wasn't planning on this, but I mean, we're here anyway. How much rows are there in between us? One, right? And between the two of you? No. How many rows are in between them? Oh, well, let's suppose that this is a row, okay? So there you go. How many rows are there in between us? Two. And between the two of you? One. Okay, so our radial distance, the dr in this equation, our radial distance is 2 and yours is 1. Now let space-time expand. And we saw that means between any 2 points, you and me for instance, the amount of meters, that's the s, becomes a bigger number now, even though the amount of rows remains 2 throughout. We get a bigger number in actual physical distance. Suppose that we make it 2 times bigger. And suppose that this was 1 meter originally. What is our physical distance later on? 4. That's now 4, yes? Yes, sure. And your physical distance? 2. Okay. But have you noticed that his physical distance and my physical distance, what is that difference? 2. Why is that 2? 4. Physical distance.
6.
That's 6. Because the amount of actual physical space between you and me have increased, but the amount of physical space between the two of you has also increased. So to me, that's an extra big effect. Do you agree with that? Yeah. So the further away somebody is, the more I see scale factor.
Oh, wouldn't that be then a problem for the cosmological principle, since like stars nearby are like more close to each other and stars far away are like more dispersed, and then it does look isotropic?
Well, there's a subtlety in the cosmological principle, namely it doesn't say, it says something about the coordinate distances between people. It should be the same in coordinate space and not in actual physical space.
Oh, okay.
There's a difference. But just to get to your original question. His original question was, if things are expanding away from each other, right? Then doesn't it mean that my ruler also gets bigger? But we've now seen that if something is very close by to me, then that amount of expansion is a lot smaller than looking at something away from me. The further something away is from me, the more space there is between us to expand, so the bigger the difference is in physical space. So why is it not an issue that my ruler also increases as the universe expands? Because my ruler is close to me and doesn't expand as much as the thing that I'm looking at. This is why you can tell that space really is expanding. Long story short, just as a general rule, if you want to know what the actual amount of physical space is between 2 points, switch from dt to ds by this transformation. Take the moment that you measure the front end and back end of the two exploding supernovae at the same time, so set this one to 0. If you can, make some simplifications as I did here, let's say you put everything on the same radial distance. And in our particular case of a Minkowski space-time, you will find that the actual physical distance, ds, the amount of meters between A and B on my piece of paper, is equal to the amount of crosshairs between my two pieces of paper, dr, times the scale factor. The more dr you have, the more physical distance you get between the two things. So I told you before, it's not terminology, there's actual physics in there. dr is the amount of space on the space-time itself. That number does not change. But the amount of physical distance, ds, that does. How much does it change? Well, depending on A and on K.
This is general, right? Not just applied to this very specific case.
Well, up to this point, this is general. And when I put the Robertson-Walker metric in, I made it specific for Robertson-Walker space-times.
So dr is not always the coordinate distance, right?
It's always called the coordinate distance.
Times also.
Yes, but the question, is there a person who measured that distance? Then the answer is no. Now back to my original point. I mean, it's a long way, but we're getting there now. Remember that I said that dr is the co-moving observer. And then I said, well, does the guy move? Because the terminology seems to indicate that the guy moves. He does not move in coordinate space. He stays at the same r position. So the amount of crosshairs in between him and the exploding supernova, that number will stay the same. But if he would actually do the measurement, he would measure his ds, he would find that he is actually moving. This is called co-moving. You're fixed on the space-time itself. It's just that the space-time underneath you is expanding. This guy is called the co-moving observer. That's the guy who measures dr. And that's it. Do you see what kind of mental gymnastics you have to do every now and then to identify who measures what in general relativity? So there's that.
And so basically we say that it doesn't matter at all where he is in the universe as long as he's the co-moving observer.
Yes, as long as he moves along with the expansion of the universe, he stays at the same radial coordinate distance, he's a co-moving observer. It doesn't matter where. By the way, you can even conclude that it doesn't matter where by the following, the cosmological principle. Because whatever holds for one guy at any position in space, in the universe, should hold for any other guy as well. So just any observer who's anywhere in the space-time, as long as he moves along with the expansion, that guy is the guy who measures dr. And there's that. Any questions about that? I can imagine this is something that has to sink in for a while.
Now we have to figure out who is that DT, right?
We already did that, didn't we? The DT guy we saw was any observer for whom the two things happen at the same position. But things for a guy who is already co-moving, things always happen at the same coordinate position, doesn't it? So the co-moving observer is not just the guy who moves along with the expansion of the universe, he's also the guy who sees two things happen at the same time. So dr is the co-moving observer. It's that guy.
Wait, at the same time? Same place? No, wait. Ah, shit. Yeah, it's at the same...
Here, let's suppose that the observer is at position A.
Yeah.
And there is two things happening at position B for this guy. Okay? Then because the two things happening at position B happen at the same 6 crosshairs away from that guy, or whatever the number was, 6, right? 6 crosshairs away. So that means that for A, the two things at B happen at the same coordinate position.
Yeah.
His physical position, the actual amount of meters that he measures, yes, that one changes by this rule.
But then it would be at the same place at the same time.
We have to be careful now. Do you mean the same coordinate place or the same physical place? It happens at the same coordinate place for that guy. It does not happen at the same physical place. The two things will explode a number of meters in between because in the meantime A has increased. Again, this is why the word co-moving is somewhat well, badly chosen because it gives you an impression that somebody is moving with respect to the space-time. No, he's fixed with respect to the space-time. He stays at the same crosshairs, but he is moving in the sense that any other point is moving away from him via the scale factor. Arthur, you had a question, I think?
Yes, but I still have to think about it, how to phrase it and how to, well, what I'm gonna ask.
You just have to parse the question and formulate it.
Yeah, it's, yeah, I'm not even sure if I understand what I want to say.
Okay.
Basically, it's the relation between the moving observers.
Yes.
So, with respect to the universe and with the inertial frames, and I'm trying to.
Wow. Okay. I see interesting alleyway here. Inertial observers or inertial frames, and yes.
Yeah, and the co-moving observers. Yeah, I don't know. There's something I'm not.
In fact, we will get to it in the next exercise. It's not phrased in that way, but I think your question is in there. So let me attempt that in a second, okay? Now, long story short, you have to do some mental gymnastics, but this is the guy who measures R and measures T. It's the guy who's fixed on your space-time, yet is still moving away in physical distance from any other person. The co-moving observer. That's the guy who measures dt and dr in your Robertson-Walker metric. So there's that. Okay. Now we have identified this guy. We can solve his equations. Doesn't that suck? We still have to do this. We've just identified who the guy is. Now we have to solve his equations. 4 equations. Fortunately, this is exercise C or D. One of the exercises is
D.
It is D. I ask you to solve these, but what I do say is, you know what? Take A to be a fixed number, because what I want you to do is identify whether things move in straight lines in a curved space-time. Now, you know, in a flat space-time, you know that if you have 2 observers and they're moving in geodesics and they start initially parallel, they will not converge to each other or diverge from each other, they will stay parallel. That's a hallmark of a non-curved space-time. Now, if the space-time in the same time is expanding, and they start over here, and they start moving over there, but the universe is need them expanding, they will diverge from each other. Agreed? That's not the divergence that I mean, because that divergence comes from the scale factor. It does not come from the underlying spherical versus hyperbolical versus Minkowski. So what I say in the exercise is, take A to be a constant. It's not a constant, it changes in time, but just take it as a constant. So whatever curvature comes out, whatever divergence or convergence of 2 geodesic lines come out, is due to the curvature and not due to the expansion. So what we're going to do, we're going to solve this, and you know what, let's make it ridiculously easy. Let's do this for a Minkowski flat space-time. In fact, that's the exercise. Minkowski flat, what does that mean?
K0.
K0. Nice stereo over there. So that one is 0, this is 0, 0, and that's it. And I said, you know what? Again, because we're only interested in whether things are converging towards each other or moving away from each other due to the curvature of space, not due to the expansion of the universe, take A to be a constant. Can we get this in stereo as well? What should this be?
Shit.
0.
I was hoping for stereo, but okay. I'm sure there is some Lorentz frame in which...
0.
Okay, yeah. Well, we needed that second measurement, otherwise there will be no Minkowski frame in which this would work, okay?
Someone that happened at the same time.
Okay. But that means that everything that has an A dot in here will also vanish. So that's pretty much everything. H is A dot divided over A. 0, 0. There's that. And you know what? We already said, well, you might as well put everything on the same line. Agreed? You're allowed to do that in a homogeneous and isotropic universe.
Zero.
Zero.
Okay, thank you.
I'm writing stuff down.
You would get this out. Okay, so this is because we happen to go to a Minkowski flat universe. This one is because we are only interested in the divergence or convergence due to the curvature and not due to the expansion of the universe. This one is because we are always able, because of the cosmological principle, to put two events on the same radial coordinate. And then all others, there's all beautiful stuff that cancels out. This cancels out, this cancels out. This is 0, that is 0, that is 0, that is 0, that is 0. It becomes much more easy, I think. It makes life simple, doesn't it? Am I forgetting something?
There's one thing in the fourth one that's.
Yeah, that.
Oh yeah, this one was also 0. By the way, this is no loss of generality. Again, you're always allowed to do this. So let's see how we simplify the geodesics now. Oh, that's easy. Second one. Oh.
Wait, why is the second one also 0? The last term is 0. The R is not 0, no. Like the term you just crossed out, that doesn't really count.
Here H is 0.
But then you still have this 1 minus 0.
Well, let's go through them. H is 0 because of non-expansion.
Oh.
So the geodesics reduced to this particular case. Now, what does this one tell you in physics, please? No, I mean, I know what it says in mathematics. What does it mean in physics?
Something moves in a straight line according to Newton's first law.
This one? This one says something about one guy's time versus some other guy's time. It doesn't say anything about positions in space.
So there's a change in time dilation.
Yes. You have time dilation because there might be dt over d tau, but it's constant. So there is some time dilation. What does this one say? The second derivative of r with respect to tau is 0. What does it say about r?
Constant length. Contraction.
It's one possibility is indeed that r itself is constant. That just means something is not moving on the space-time. It's correct, but we can do more general, right? I mean, if r is a constant, then second derivative is certainly constant, but this one works as well. Some number times tau. Agreed? These two don't tell you anything. Just tells you 0 is 0, which is correct. I mean, it's good. It's mathematically sound. 0 is 0. Is this a straight line?
No, with that. With somebody else.
Yes, it is, right?
Yes, it is.
Yeah.
So we find that in Minkowski flat universe, that is not expanding, so we're excluding things happening due to expansion. Things move in a straight line. Note that this is the coordinate distance. It's the amount of crosshairs between A and B. So that number now increases. Something is actually moving on the space-time away from the other guy. If you want to convert that number, the amount of crosshairs at any point in time, to the actual physical distance, I just erased it, you have to multiply this number by A, by the scale factor.
But it's 0 in this case.
No, not A was 0.
Sorry, the derivatives.
Yes. So in this case it will be constant. But if we go back to our original case, it will probably mean that the amount of distance itself is increasing as well. So it's moving on the space-time. At the same time, the space-time is itself expanding. In astronomy, there's actual terminology for this. Things moving away from each other due to the expansion of space-time, this is indeed what gives you the redshift and the blue shift. Would be a redshift in this case.
Is that a relativistic Doppler effect?
No, that is a second effect. You're adding two effects now. The Doppler effect is when a wave on its way to the observer, while there's a relative motion between the two observers, it gets a Doppler shift, the usual one, and on top of that, the space underneath the thing is expanding. So it gives it another amount of shift. That's a relativistic Doppler shift.
Well, I thought the Doppler shift was directly caused by the expansion of the universe, to the fact that there's more distance for the wave to travel with the same energy that originally had it.
Yeah, but that's what we have here. That's what it says. Remember, this is only the physical distance between.
You said it happens for there's two different things that affect the properties of electromagnetic wave.
Yes.
The relativistic effect and the Doppler effect.
Yes, there's both of them. And when people talk in astronomy about redshift, they mean the one due to the expansion of the universe.
And what's the relativistic Doppler effect then?
That's the combination of the two. The usual Doppler effect, because the source and the receiver are moving with respect to each other, and on top of that the underlying space is increasing. It's a relativistic Doppler effect. So there's that. So I mean, complicated equations, but if you just choose your coordinate frame in the right way, something somewhat easy comes out. So there we go. One more thing, the time dilation. We know it's a fixed number, right? Do you know what the number is? Somebody who wants to guess that's a gamma, maybe? Because of Minkowski spacetime? In normal Minkowski spacetime, dt d tau would be gamma. Question is that the same thing here? Now, is there any way that we can find out what the number is without guessing? Might be on the board somewhere. Might be some equation I haven't used yet.
One of the just below the geodesic equations, the normalization of form velocity.
Yes. Right? Because any motion in space-time has to obey this extra condition as well. Let's apply it here. This is the number that we're looking for. Ut is dt d tau. We already know it's a constant because the geodesic equations told us. Now we looked at a very specific case in which this is 0 and that is 0. So that means that minus ut squared plus, remember that we were looking at the specific case of Minkowski flat expanding spacetime. So this is just a squared over 1, so that's a squared. UR squared, and that whole thing should equal minus c squared, but we're now in c is 1 units. So there you go. Okay. Make it a little bit more beautiful. Oh, I love this. Ugh. This is not the part that I was just being so happy about, the minus sign. This is me just multiplying left and right with minus 1. UT. This is the number that I'm looking for. Let's see if you see why I do this. Do you agree with this part? No physics, just mathematics.
Is it the drdt you just wrote down?
Yes, this is not the rd tau anymore, it's the rdt.
Because ut is dt d tau, and if we multiply it with, well, multiply, not actually multiply, but can just kind of cancel it out as with actual fractions.
Yes. I understand why you're hesitant, because mathematicians don't like that you call derivatives fractions.
Yes.
But you're using this.
Yeah.
Agreed? It's just, let's put the mathematical correct term in. It's a chain rule of differentiation.
Okay.
And this thing is what I wrote down here, and this thing is itself ut again. dr d tau is the distance measured by the co-moving observer divided by the time of the co-moving observer. So this thing is really just the velocity as measured by the co-moving observer, the guy who's standing still with respect to the space-time. Let's clean up everything, because you can now take ut squared out of the brackets, 1 minus a squared. This is a velocity, velocity squared equals 1. Does it start to look familiar now? Gamma-ish, you're right, the ish is well put. Very well spoken. There you go. I left the c's out because c's for unity, and if you want to put the c back in, here it is. It's indeed gamma-ish. But now you have to take into account that while things are moving away from each other, the universe is expanding, so the amount of gamma increases.
So it's like general relativistic gamma?
if you want, yeah, sure. It's don't take this as a general rule. It holds in our Robertson-Walker case. Okay? So by using the normalization of forward velocity, we actually know what the time dilation is. It is gamma-ish. You take the velocity as measured by the co-moving observer, multiply it by the scale factor, then you get this actual physical velocity. This has to be very clear to you now. V is the RDT, the co-moving coordinates. That's the velocity is measured on the space-time. But on the space-time, in order to put that, to turn that into actual physical distance, you have to multiply by a. So this thing is the co-mover velocity, and multiply by a gives you the actual physical velocity, the actual physical v, the one that you would actually measure if you were not the co-moving observer. And then this just becomes the gamma of the non-co-moving observer, the one that actually does the measuring. So it's not just gamma-ish, it really is gamma. You just have to keep track of the co-moving observer and the actual physical observer. Whew. I think it's time for a break. And if you recall, this is what you get at the moment that you assume a Robertson-Walker metric, one of the three, right? Spatial, flat, spherical or hyperbolical, depending on the k. And if you assume that the whole of the universe is filled with a fluid that has the same pressure and density everywhere, might change in time, so these are time-dependent functions. This is the density, this is the pressure. If you put all of this into the Einstein field equations, there's very little physics there, it's just working out the mathematics. You will ultimately find two equations that tells you how the scale factor evolves in time. You should read this as differential equations, that if somebody tells you what the density is, what the pressure is of space-time, of the stuff inside of space-time, then you can solve this, and ultimately you will get out A as a function of t equals such and such. And as you now know, once you have A, the scale factor, you can take any 2 points in coordinate distance, note my words here, in coordinate distance, and translate them to actual physical distance. Because this is what A does for you. It takes coordinate distance, the amount of units, crosshairs in between any 2 points in your curved space-time, and scales it up to the actual physical distance. So this is a key concept. One of the main issues in cosmological exercises is finding the scale factor as a function of time, because from that moment on you can do your cosmology. Okay, now we already did one of these. We said suppose that you have rho equals, or is energy divided by a to the 3, y a to the 3. Again, this is physical distance now, physical volume. Amount of energy per volume, put this in, do the calculations, and you will find that A is t to the power 2/3. We did this last week. So this is how you do cosmology. Now, we're going to look at a very special case here. P equals minus rho. Try to give some interpretation to this stuff that might have a positive energy density, so this is a positive number, this many joules per cubic meter, but then it has a negative pressure. pushes inward or something like that. If you would fill the balloon with that stuff, the balloon would shrink. That's weird. Strange stuff. Doesn't push out, it pushes in. Now, let's assume that this stuff exists. Very hypothetical, but it does lead to something that we can actually measure that the universe does, which is expanding in accelerated fashion. And you can get this to work by putting this one in. So the question, just rewriting everything that I had before. Question, how would you try to find A as a function of time? How would you do this? Just as a mathematical exercise. Bless you. Little physics is involved. This is just a mathematical exercise. Can you solve this? Any ideas how to do this?
And if we plug this in, or
Well, ultimately, I just want to know what A is as a function of time, given that my fluid that fills the universe has this particular, very peculiar equation of state, as it is called. The thing that has a pressure that is minus its energy density. The question is, what would my scale factor be? What would A be as a function of time? How would you get this out?
So how you have to rearrange it to get P and the density and the pressure to have that relationship within those equations?
No, I'm giving you the equation, so you already know that it has this relationship. My question is, what is A? The big unknown is this one. A is a function of t. This is the one that I want. Given that this is true, to make it a little bit more easy, the exercise said, consider the universe Minkowski flat, expanding but Minkowski flat, so k is 0.
So you just fill in values, right? For yeah, either rho or p.
Okay, so which one should we do?
Yeah.
So do you prefer to have, yes, I'm going to put this one into here. Do you prefer to have everything expressed in pressure or in density? Both are fine, it's just density, okay. That's what I would do too.
But
So that means,
it's not easier.
sorry?
It's not easier if you have afterwards combined both equations.
There we go. There you go. There's a nice program. At the moment that you put this into here, so that all my p's are now replaced by minus densities, then this one would turn into an equation that only has densities. This one only has densities. So you can squeeze them into each other, get one equation, and hopefully solve that. So there's a program. Let's try it. Rho plus 3 times p, but 3 times p is itself minus rho. So that will give you rho times minus 3 times rho, gives you minus 2 times rho. So you get this. Plugged this thing into there.
It's technically the same as the other equation we have.
Yeah, look at that. This thing has now become that thing. So it means that we can eliminate your rho. By the way, it also would have worked if this wasn't exactly the same thing. As long as you have a rho in both equations, you can squeeze them into each other and get something. In this particular case happens to be very simple. They already are exactly the same thing as right-hand sides. So that means that 8 squared should be 8 dot dot over A. And 8 squared, if you recall, is itself so here's our differential equation. Note how beautiful it looks. There's no stuff hanging around, g's and numbers and such, and pi's. It's really just A expressed in A. Just cleaning up a little bit, mathematically. We're looking for a function A as a function of time such that if you take its first derivative, you square that number, you get back the second derivative times itself.
Should it be something e, the exponential?
Something e-like.
E-ish.
E-ish. Okay. Sure. It's a nonlinear differential equation, so that means no standard tricks. You just have to be ad hoc and try to think of something. You know, why would you choose e as something?
Because its derivative is still equal to itself.
Yes.
Maybe times a constant depending on what the power is.
I very much agree.
And in the case that there is like no power, if it's just like e to the t, you already get there.
Well, it does say a derivative equals itself, or so, two derivatives equals itself, or something like that. But it does come with a square, and e to the power of something derivative do not equal them their own squares. It equals themselves, not their squares. We can still try it though, see what happens. Okay, so here's a guess. I call this an Ansatz in nice German, with a capital A, just like they do in Luxembourg. They capitalize their nouns. So this Ansatz says, well, it's something times e, and then we have to put a number here, and I don't care, some variable. Lambda. Is it a coincidence that you're choosing lambda?
Yes.
Okay. Okay. So this is our Ansatz. Going to check whether this happens to be true for some lambda. Okay, help me out. What would left-hand side be? So take derivative, take it square. Tell me what it is.
Lambda squared times e to the power 2 lambda t.
How about this? Let me put one step in between. Right, here's the derivative. Then you square that thing, that gives you lambda squared e to the power 2 lambda t. Okay, so that's this side. Let's see if the other side is the same thing. If so, then our answer was correct. A times a dot dot. A, well, we guessed it was a e to the power lambda t. And this thing, second derivative?
This is lambda squared times e to the power lambda t.
That's correct. A is this thing. A dot dot is that thing. Clean up. Now look at this. It works. Now isn't that beautiful? So apparently, yes indeed, this is the correct solution. Huh. So tell me, expanding universe, contracting universe, let's do some physics. What does that mean? We have found that under this condition, we found that the universe is given by this exponential function as a function of time.
Yes. So we don't specify lambda.
No, apparently our equation does not specify lambda. It just tells you that it's exponential.
Yes.
But then, depending on whether lambda is bigger or smaller than 1 or 0, it will make a difference.
Yes, because in one case, it will be an expanding universe. If lambda is a positive number, if lambda is a negative number, it will be a contracting universe, a universe that tends towards 0, where scale factor tends towards 0. Okay, so we find this. Agreed?
Does that mean we need some sort of physical interpretation of what lambda is?
Yes, but we're going to find it in a second. For now, I want you to appreciate that we found that as far as the combination of these two equations is concerned, we find a universe that is either contracting, if lambda is a negative number, or it's increasing in time in an exponential fashion, if lambda is positive. The mathematical purists will come along and say, but what if lambda is imaginary? Okay, then you have a complex exponential, which means sines and cosines. You would have some sort of oscillating universe. Okay. At this point, every lambda fits. As long as lambda is not 0, you should be able to use any lambda. So we haven't specified lambda yet, but we do see that there is something exponential going on. So here's the correct solution. my claim is it's an expanding universe. Lambda is bigger than 1, than 0. It's a positive number. Is there any way that you can tell?
There would probably need to be more minus signs somewhere in the other derivatives, right? Because if lambda is a negative number, then taking the first derivative will
Mhm.
mean that it will be scaled by a negative number, and then taking the second derivative will mean that it will again be scaled by a negative number, so there would be a sign difference between the second and the first derivative.
Yeah, but you wouldn't see it here, would you? I mean, whatever lambda is, plus or minus, because of the square, it will always come out as plus. And here, because you take 2 lambdas because of the derivative, that also always gives you a positive number. So you're not able to tell at this point. So really, as far as we can tell, you could have this as a solution with lambda plus number, but you might as well have this with kappa, and then take kappa as a negative number. Or let's put it like this. Lambda and kappa are both positive, and maybe some combination is positive. And there's no point in trying to put this back into these equations, because of the square in the second derivative, you will always get whatever lambda is, it will always come back as a square. So there's no point, just by looking at these two, which of these is the correct one. Well, there's quite a difference between the one, because one of them says an expanding universe and the other one says that it's a shrinking universe. So there's, I mean, I really don't know if there's any bigger difference in predictions physics than this. Expanding or contracting universe. So what should we do?
Leave it like this, and then say that it can be both, and we're always going to be correct.
Yeah, but okay, this is the fortune teller,
Yeah.
right? Okay, yeah. It's not as bad 10 to the power 200, but it's 2 to the 10 to the power 0. We have 2 possibilities. We don't want 2, but we want 1 prediction. Now, if you go to classical mechanics and you find that your differential equation has 2 solutions, what do? Typically, differential equations have 2 solutions.
Exclude the negative result.
If you have physical reason to, yes. Sometimes you find, well, this happens at a negative time, then you throw it away because no such thing as a negative time or such. How about we add them together? My prime example of classical mechanics, second derivative equals minus no derivatives. 2 solutions. X is cosine or x is sine. Now, which of the 2 is it? Well, if you just add them together, both work. This is what you typically do. If you have a second order differential equation, what you typically hope is that if you have the 2 solutions, that you can add them together, you get the general solution. There's a cosine part and a sine part. Maybe in our space sine, you have an expanding part and you have a non-expanding part. There's an issue though. A mathematical difficulty difference between this differential equation, the one that we were solving, and an equation like this.
The square.
It's the square. Our differential equation is nonlinear. And nonlinear means that the function or its derivatives only appear to the first power, and here it appears to the second power. Now, this idea that if you have 2 solutions, then that the sum of these 2 things is itself a solution only works for linear differential equations. We don't have a linear differential equation, so it's not certain that this combination is also a solution. They are a piece, but their sum might not be. I say might not be, because the mathematical claim is, here it is guaranteed that the sum of 2 solutions is a solution. Here it is not guaranteed for a nonlinear differential equation. It might still be the case, but it's not guaranteed. How about we just check it? We could just go and check it. Let's check it. I feel we should check it. Yeah?
Let's check it.
Let's check it. Okay, let's do some checking. So our proposed solution is, let's do it like this. About this. I say it's a linear combination. Could have chosen as A and B. I try to be consistent to say if this is a lambda, then put a capital lambda here or something like that. Let's see if we can make the whole thing, the sum of these two possibilities, a solution. So that just means we're going to put this back into here. See if there is a lambda and big kappa such that this works. So let's do it very quickly. A dot squared would give lambda big lambda e lambda t plus minus small kappa big kappa. Then we have to square the damn thing. There we go. Am I going too fast, or do you believe me when I write this down? It's just taking the derivative, taking it square.
Needs to be 2 still.
It's over here. There it is. Thank you. That's this side. This one. So that's left hand side. Let's do right hand side. That's a times a dot dot. Again, I might be going a little fast through this. It's really just because it's just basic mathematics. This one times the second derivative. Okay. I think that's correct. Multiply everything else. This times this, that times that. Those are the terms that I have now. Kappa lambda squared lambda e to the power lambda minus kappa t, and finally I get small k squared, big K squared. Okay, wow. Again, this is me just writing out the mathematics. In order for our proposed solution, the sum of a contracting and expanding universe, these two, in order for this to be true, I have to make sure that this thing equals that thing. I have to choose my lambdas and kappas such that this works. Can we do it? Let's take out the old red marker of cancellation. Because what I see is this thing is already equal to that thing. So we don't have to worry about this one and that one. These already are the same on both sides. Same thing with this one and that one. Agreed?
Yes.
So the only thing you have to make sure is that this thing equals that thing. Can we make that work? Is there any way to choose our kappas and lambdas such that this works? While you ponder this, let me make some space.
Sorry, I missed that part. Did you already cancel those out, or do you want them to?
I want this one to be exactly the same thing as this one, so they are the same on both sides of this equation. That means that it works.
And if you set lambda and kappa to 1,
Which lambdas? The small ones or the big ones?
small one, and the small kappa 1.
Okay.
Yeah.
E to the power 0.
Well, let me first clean up a little bit. Left-hand side we saw is now -2, small lambda, small kappa, big lambda, big kappa. Sorry, Panos, but this is really the best Greek I can squeeze out. This is left-hand side, and we want it to be equal to right-hand side, otherwise our proposed solution doesn't fit. And our right-hand side, as we saw now, is big lambda, small kappa squared, big kappa, plus big kappa, small lambda squared. Yes, okay. There you go, e to the power lambda minus small kappa. T. If we can make this work, we are good. I see some beautiful cancellation coming up. Agreed? Well, this thing is on both sides. You can cross it out as long as it's not 0, but you don't have to worry about that with exponentials. They're never 0. I see an overall lambda here, which is also there. So that one cancels out on both sides. Agreed? And I also see a kappa on both sides. This is a big kappa or a small one. That's a big one. It's a big kappa. I see big kappa on both sides. That cancels out. There, there, there.
Are we allowed to assume that they aren't 0, big lambda and big kappa?
Well, that means that if we assume that they are 0, that means that we never used it to begin with. The fact that I wrote this down.
But that might be an option, right? I
This
mean,
might-
No, but we have already done it. At the moment that this is 0, big kappa is 0, we've already seen that this is a solution. Do you agree?
yes, okay, because
So a piece are a solution, and a piece you might also say the other amplitude is 0. We've already seen that those are solutions. By writing it down as this particular combination, I'm assuming that they're not. So this is why I can divide them out on both sides. Long story short, I see something like this. Should equal kappa squared plus lambda squared. Can we make this work? Is there any way to choose our kappas and lambdas such that this comes out right?
Minus 1.
This is correct, isn't it?
Yeah. I was just thinking.
No,
If either
Either one of them.
if
has to be
either
minus.
lambda is -1 and k is 1, or
Yes.
other way around.
Well, you can tell that at least one of them has to be negative,
Yeah.
because otherwise you can never get a positive number out. Okay? Alright. Let's pursue this a little further. Let's solve for, let's see what we have here. Let's solve for kappa. We know that kappa is a function of lambda in a particular way. Let's try and see if we can find what that is. We can already tell that in order for this to work, a expanding universe and a contracting universe, the amount of expansion of the one has something to do with the amount of contraction of the other, because they're related to each other. You just have to find out what that is. I will do it like this. Plus 2 lambda kappa plus lambda squared. ABC formula or something like
It
this?
does resemble, it's a
Yeah.
polynomial.
It's just polynomial, right? It means it's ax squared plus bx plus c equals 0, with x being kappa, a being 1, b being 2 times lambda, and c being lambda squared. And then use your typical polynomial formula. That gives us kappa is 1 over 2 times a, which is 1 in our case, 1 over 2, minus b, minus 2 lambda, plus or minus b squared, which is 4 times lambda squared, minus 4 times c. This is just me going through the algebra. Cancels. There's some beauty in here, isn't there? If you just go through your basic algebra that you picked up somewhere when you were 15 or so, you will find that yes, you can have a mixture of an expanding universe and a contracting universe, as long as the amount of contraction is minus the other one. But wait a minute, that gives us something interesting.
Just intuitively, does it mean that there's no net contraction or expansion at all?
Why?
Because it's like you have an equal expanding term of expansion that is numerically equal to the term of contraction.
But wait. We had a negative kappa here, agreed?
Yeah.
And kappa itself is negative lambda.
Oh, yeah.
So what we really have here is another expanding term.
Yeah.
It's an expanding universe. There you go.
Interesting.
Now, if we know that this is the same expansion as this one, might as well just put it together, make it just one big ae to the power lambda t. Okay, don't worry about the splitting up in a one part and a second part. We now have really identified that it's something that goes like this. Question now is, what is lambda? I mean, what is that number? That's the next question. Back to our Friedmans. H squared equals such and such. Go. H is itself a dot over a. You have to square it. That's the left-hand side of the first Friedman equation. Put this thing in that we've now found. We find that well, that's very beautiful. Gives you lambda e to the power lambda t divided by e to the power lambda t squared. Drops out, drops out. Lambda squared equals what?
Right hand side.
Yes, which is 8 pi g over 3 with some c squared somewhere in a row. Do you agree? But that means that lambda really is that thing. So what we have now is, forget about the mathematics, just the physics. What we have now here is, under this assumption, you will find an expanding universe, exponentially expanding universe. Lambda is a constant, right? We put that in. This only works if lambda is a constant. Then the Friedman equation tells you, yes, but that lambda has to be related to this thing. So the amount of expansion depends on how much energy there is in the universe. So this stuff that obeys this strange equation tells you the more of it you put in it, the stronger the universe will expand. So whatever it is, it's something that really pushes everything out. And the more you put into it, the more it squeezes out. The more it pushes things away. That's one thing. One other conclusion that the exercise asks you to draw is, show that rho is a constant. It's an energy density. I never said how it becomes bigger or smaller in time. Just said it is equal to minus p. Can you now see that it must be a constant? I think that's exercise C. Show that rho must be a constant. I did not put that in. I only said that it was equal to minus p. I never said it was time independent. But now you should be able to draw a conclusion. Wait, but it's constant. Why is that?
Would the derivative not be different?
Yes, thank you. That's all I wanted to hear. When I use my ansatz here, and I plugged it in and I went through the calculations, it only worked when lambda was a constant. So my solution that I find here is true if lambda is a constant. Then the first Friedmann equation tells you, oh, and that constant is proportional to the square root of the energy density. Therefore, the energy density must be constant. So whatever dark energy is, it has this very special property that its density does not change in time, even though the universe itself is expanding in rapid fashion. Now, yeah, I mean, I can see the face that you're making, and what is the confusion here?
It doesn't make sense.
Why is that?
Because
No, put it in words. One of you.
Like, I think I have the same confusion as you, but I don't know how to put it into words.
You say it's an expanding.
So it's getting bigger,
Yes.
but the energy density stays the same.
Yes. So energy density is the amount of energy per volume.
Yeah.
The volume is increasing,
So the
but the energy density stays the same.
Yeah, okay, because there's still the same amount of energy in the volume. So
No, yes, but the
Yeah,
same
but
amount of
there's more
energy
volume.
in a bigger volume, in an increasingly big volume,
yeah.
would make a smaller density.
so energy is created out of nowhere.
That's one way of putting it. I'm going to, well, we're breaking some laws here, yes? Creating
Yes.
it. So as the
Yeah.
universe expands, it refills itself with energy or something like that.
So the entropy decreases over time.
Why is that?
Well, it expands, but the energy density is constant, right?
The energy
Okay.
density is constant,
Yeah.
yes. What if I drop a term, and maybe from the term you can see a way out of this confusion? The term that another term that people use for dark energy is vacuum energy. Does that help? Does it give away a little?
Same as 0 point.
Oh,
energy.
yes, that's another term, but you might know that there is a huge issue there. Because if you calculate the 0 point energy, so the amount of photons that fluctuate in and out of existence by quantum mechanics, you also find the number for rho, but it's about 10 to the power 100 off, literally. So it's an unsolved issue. Where the stuff comes from. Vacuum energy. Now, everybody sees the issue here. You have more space, yet the amount of density stays the same. Here's the solution. One solution is energy gets created as the universe expands. One other option is, how about empty space itself already comes with pre-made energy in it? Every time that you get an extra cubic meter, that stuff already comes with its own energy.
So when the universe is expanding, the new expanded space
Yes,
time
this
has-
extra block of volume that you
yeah,
get.
has energy in it already.
Yes.
When it's expanded.
Yes.
So
So
density scales together with the expansion of the universe.
Yes.
That's the
So
computer.
Kind
So
of
the
creating
expansion
energy.
creates energy.
Yes
Out
and
of
no.
nowhere.
No, well, yes and no, because we have the issue here. Are you talking about creating energy in coordinates? You're not creating energy.
Yeah.
Because every time that the universe expands, in coordinates, the amount of units, the amount of crosshairs in between any 2 points has not changed. So in that sense, you're not creating energy. In that sense, you would expect it to be a constant. So in coordinate sense, you are not creating energy. Yes.
And so just to be clear, this result doesn't imply that new space gets created, but eventually there will not be enough energy to keep the universe together.
Yes, that is very much alike. And in fact, that is part of the next question that I will go to in a second.
Big rip or big freeze.
It will be a big rip in this case, or if you will, big freeze. They're related. This is the solution that people typically take. I mean, if you just follow the math, this is what comes out. If you believe in the Einstein field equations, which gives you this, and the cosmological principle, because we put that in, and you believe that you can apply general relativity to the whole of the universe, and you assume that this exists, very big assumption there, okay, then you will find that the universe, with every cubic meter that it gets because of its expansion, also gets a certain amount of energy that comes with every cubic meter extra volume. This is the route people take. Now, why would you assume this? Well, you wouldn't, except that this is measured. This is what the universe does. In fact, it has a name. This is called the De Sitter universe. It's named after a Dutch astronomer called Willem de Sitter. Or De Sitter expansion.
So, can we say that energy is then basically sort of space? Or
No, don't laugh. That's actually true. Yes. Or you could say with every cubic meter you get energy. They're
Automatically.
Mathematically, or automatically. Yes, you cannot separate. You cannot get one without the other. But then again, why is that straight? We saw before in special relativity. Well, you didn't do this with me, but with Chris. That if you add mass to something, you also add energy, right? Now we're all used to this E is mc squared. But remember what strange new idea that was back in 1905 when people said, wait a minute, you can get energy just by adding kilograms to something. The kilograms don't even have to do something. They don't have to move around or float or have a velocity. If you put something here, that thing already comes with its own energy. That's the same kind of reasoning here. Matter comes with energy, and this says, well, empty space itself also comes with energy. Yes?
so does that also mean that matter and space are basically? I'm just linking
No,
it.
I understand the question. As in, that matter and energy are somewhat equivalent with a c
I
squared
know
and a
that they're
gamma.
derived in two completely different ways.
Yes, but you can make some sort of comparison. You can say, well, there's E is mc squared with a gamma somewhere in between. Tells you that if you have matter, you also get energy. So energy and mass are equivalent. But now we find that energy and empty space are also equivalent. So therefore, mass is equivalent to empty space or something like that.
Yeah.
It's a strange situation, isn't it? But here's the thing. If I have a universe here, and I add some matter in it, then we go back to our exercise of last week when we calculate a universe with where you put energy, matter in, it expands, but it goes slower and slower. That's what we did last week. We found the scale factor, t to the power 2/3. But if I have a universe and I put some extra empty space in there, it starts to De Sitter expand. So you can sort of talk your way from matter being space, but they do different things to the universe.
So basically the energy you would put in because of the the space you would put in extra that would give you the extra energy. If you have matter, that energy would basically go to the matter, so the extra space would not have the energy to expand. Okay, that was a very poor explanation. I have it in my head, but I can't get it out.
Well, while you ponder this for a second.
Yeah.
The last question that the exercise asks of you is, well, suppose this is all if you have a universe in which there is only this strange stuff, which we now identify as empty stuff filled with empty stuff, because apparently that's what this does to you. Let's suppose you have a universe where you put a little bit of matter in, if you want a little bit of radiation, or a lot of radiation, a lot of matter, but also some of this dark energy stuff. Let's see what happens there. But you had a question, I think.
Yes, so if we assume that energy is an inherent property of space that comes with it, do we also assume automatically that space is made of some kind of fabric or something?
Okay, that is a good question. Normally you can only assign energy to stuff, and now we're saying we have empty stuff. So does that mean that we sort of have to assume that the universe itself, it's the amount of volume that there's in there should be seen as stuff? That's sort of the question, I think. Yes.
Yeah.
Yeah.
I don't know. It's probably a bit far-fetched, but I'm having trouble to just associate an energy with an empty space.
Yes. But why is that?
Because you say empty space should come with its own inherent amount of energy, but then if you have 1 unit of empty space, how much units of energy are going to come with that unit of empty space? Or will there be different energy densities for different densities of space?
No.
I don't really know.
No, you get the same amount. This is again the ghost of the cosmological principle. Any amount of volume comes with the same amount. Well, not any amount of volume. The volume taken anywhere from space comes with the same amount of inherent energy. By the way, this is a nice way of putting it. Inherent energy. Maybe that's better than saying vacuum energy. It's the energy of the vacuum, the energy of just having volume. And I'm stressing this point, well, I find this strange. Yeah, but then again, in 1905, people found it very strange that if you have a kilogram that doesn't do anything, that already came with this energy. You don't have to heat it up. It doesn't have to move, doesn't have to wiggle. It came with energy. Now, we now find, if you take this seriously, that empty space also comes with energy. Again, does that mean that energy is therefore, or empty space is therefore the same thing as matter? No, because matter makes the universe contract. Or not contract, but slow down its expansion, whereas empty space makes the universe expand even faster. Yes?
Just to clarify, we found that the energy density stays the same while the universe is expanding, so I have reached the conclusion that that means that there's energy intrinsic to empty space. Like what I picture is a balloon that just gets bigger and bigger, and the thing that holds together gets weaker.
Yes.
Because the same force.
Yes, okay, thank you. I mean, Panos, that was exactly the picture I wanted to draw. That's one of the exercises. Suppose that you have a universe where you put a little bit of everything in, what will happen? And this relates to your question. Let's draw this.
But before that, why is the conclusion that empty space has energy from that result?
Yes. Because the fact that the energy density remains constant, even though the universe is expanding, so you get more volume, even the fact that that happens, the universe gets bigger, more volume, and you yet have the same amount of energy density, means that the amount of volume that you put in already comes with its own energy.
But there's the same energy, there's less energy per unit because you get more space. I mean, it's the same energy per unit, but there's more space to spread it over.
Yes.
So, just my understanding of density implies that it would just, like a gas, if you let it expand, it will get less dense as it expands.
How about this? You have a barrel of gas, yes? And there's a certain density, so many particles per cubic meter. And I expand the barrel, but I don't put any extra gas in. Then the density of the gas becomes less. Agreed? Now what if I expand the barrel and at the same time put more gas in such a way that it counteracts each other? That's what happens here. Every time that you expand the barrel, some more gas gets in. Actually, not too long ago, in January, finding out what this stuff has been made one of the key things that the APAC, that's the European Astroparticle Physics Convention, I forget what the abbreviation exactly stands for, have decided to make one of their most important things that they're going to work on. And I had to explain this on TV in January. It was in Dutch for people who want to look it up. And I had to explain how this works. So what I did, I brought some lemonade. This is maybe a metaphor that works. Okay, you have a glass of water and you put some yellow lemonade in there. This is literally what I did on TV. Some yellow lemonade. And the amount of water in there is the amount of space. And the amount of lemonade, the syrup, the stuff that you put in, the sweet stuff, is the amount of space. At the moment that it's the amount of matter. At the moment that I pour more water in, I make the universe expand, as in get more volume, but I don't add more lemonade. You will see that the color at some points fades away and it becomes almost transparent. All the yellowish goes away. But what if I, instead of pouring in there water, but I pour yellow lemonade in there, so water and already with its own syrup, then I can add as much as I want. It will the glass will, I mean, it will expand, but it will still have the same amount of sweetness, the same amount of yellowness. That's what this stuff does. With every cubic meter, you also add extra energy. This is the conclusion that you necessarily have to draw if you take this seriously. Now, again, suppose that you have a universe in which you start out, here's energy density, you start out with a certain amount of radiation. So here's time, here's radiation density. Photons.
Already question 5, right? We're combining all the...
Yes, we're combining everything together now. And suppose that you also have a certain amount of starting amount of normal matter. For no particular reason I said there was less density of normal matter than radiation, which is actually true, by the way, at the beginning of the universe, for technical reasons that are not important right now. I know how these will go as time goes on. They will decrease. Right? More volume, time goes on, universe expands. So that means less density for these two things. I can in fact tell you what these things are going to be, because if you recall, we took this for our matter density last week. But we also found that for matter, this was true. For a universe that expands due to the presence of matter. This again, exercise last week. Put this in here, you will find that the density of matter goes 1 over t squared. Exercise 4 says, or maybe it'll see. Exercise 3, excuse me, says, well, do the same thing for radiation. And if you've gone through that exercise, you will have found that the radiation density goes to 1 over a to the 4th. A to the 3 because it's a volume, but because the energy decreases for light because of the expansion of the universe, therefore a bigger wavelength gives you less energy, gives you another factor of the scale factor, 1 over 4. You go through the Friedmann equations, and you will find that A is this. If you haven't done this exercise, I highly recommend it. Just go through the exercise. Then too, you will find that the radiation density goes to 1 over t squared, just like matter. Again, this is an assumption because you know what the density is. Go through the Friedmann equations, that gives you this. Plug them into each other, you get 1 over t squared. Radiation, 1 over a to the 3 because it's density, an extra a because of the redshift. Go through the Friedmann equation, tells you a is square root of t, plug it in, 1 over t squared. 1 over t squared, 1 over t squared. And they both go to 0 asymptotically as the universe expands. This is what you expect, right? The bigger the universe, the less density you have of each. Now suppose that we start with a little bit of dark matter in this universe as well. I don't care which one. How much? Let's suppose there is an enormously small amount of dark energy. What does this line do? Does it go up? Sure.
It doesn't mean this is a straight line, like a horizontal line.
Now which one will win?
Horizontal line.
The horizontal line. Well, that sucks. Because it means if you have a universe with only the smallest amount of dark energy in, if you wait long enough, it will become the dominant amount of stuff in there. The other stuff is still there, but it's very diluted. And you need the amount of dilution to tell you what the universe does. The Friedmann equation tells you how the universe expands based on its density. Right? It's all in densities here. But that means that this stuff that tries to grab the universe together, Panos, this is what you were saying at some point. The normal stuff in radiation tries to hold the universe together, tries to slow it down. Right? These things slow down. If you take some derivatives, it tells you that the universe is expanding but slowing down. But unfortunately, due to the expansion, the influence of these rows, the radiation row and the matter row, becomes so small that they don't do much anymore. This one, the dark energy, never dilutes. It's always constant. So if you wait long enough, at some point, you might as well say, I have a universe in which there is no matter or radiation anyway, or it's so diluted that it doesn't do anything anymore. And this one is never diminished. Now what does the universe do if effectively it only has dark energy in it?
It will just expand.
It will just expand forever, increasingly so because it's exponential.
Yes.
Well, that's a sucky conclusion for the end of the universe. Everything will move away and never come back. Regardless of how much matter or radiation you put in there, dark energy will always win. That sucks. Yeah, I mean, isn't that a sad conclusion to the universe? Everything will move away and never come back? I have two things I want to add to this. By the way, this is the end of the exercise. Let me add two more things, Panos. That's a sucky conclusion. For one thing, there's a famous cosmologist, Lawrence Krauss, who was one of the first people who suggested that empty space comes with its own energy. And then the measurements were done and appeared that it is true as far as we can measure. And he came up with a very sad conclusion of this. He said, well, that means that literally everything at some point, if you wait long enough, dark energy will have taken over, everything will expand exponentially, go faster and faster. At some point, galaxies and such will be moving away so fast that light cannot catch in on this, cannot catch up. Because it's exponential, it goes faster and faster without bounds. But light is stuck to this 300,000 kilometers per second, and if things expand faster than light can go back to you, literally light will not reach you anymore, never.
So the whole observable universe will eventually become a singularity, basically.
It will not become observable anymore.
Yeah.
Because everything that is observable, all the light, will have been moved out. The light that's already here gets redshifted, and the light that is on its way here doesn't go fast enough to actually reach us here, because the underlying universe is expanding faster than the light can catch up. And that means that at some point, if you wait long enough, a species of aliens that still have to, climb out of their bacterial ancestors, right? These people who don't exist yet. Suppose in 3 billion years, I have no idea what the number is, but suppose that in 3 billion years we are at the Sitter stage, where everything goes exponentially. Then at the moment that these people have evolved in such a way that they become scientists, and they look up with their telescopes to the sky, they will not see any other galaxies. Or constellations. They will literally think, oh look, we're exactly one planet. Well, it's not one planet, because it works on bigger scales than this, 100 megaparsecs, right? So that means our own galaxy, they think, well, the universe consists of exactly one galaxy, and the rest is empty space. And it doesn't matter how well they measure, how big they make their telescopes, they will literally not ever see any of the other galaxies, not because the telescope's not good enough, but simply because the light cannot reach them anymore. And the sad thing that this Lawrence Krauss says is that means that this generation will have all this physics lying around that they will never ever be able to find out.
Yeah, I was just going to say that, like, there's no way they can ever figure out any of this without...
No. Mm-hmm. It's even worse. Most of our understanding of this stuff comes from the cosmic microwave background. Right? This is how we get most of our numbers from cosmology. But if those numbers get redshifted because of the expansion of the universe, they get redshifted asymptotically to zero, they cannot measure the cosmic microwave background anymore. Well, this is one of the reasons that we know that there was a cosmological principle to begin with. Now, without a cosmological principle, you cannot get the Big Bang. So these people would have no idea that the universe even started with the Big Bang ever. For them, the universe consists of their galaxy in a complete empty void that has always existed. They would come to the wrong conclusions, and not because they're doing anything wrong, simply because all of the information that they need has been moved away to infinity and never came back.
And who says that this
Yes.
doesn't apply to us?
Who says that there is always enormous amounts of information that has already moved out of our observable universe? Not because of this, by the way, because the expansion is not that big yet. But this is a sad conclusion. There might be answers laying around that we simply, literally cannot reach. Yeah, that sucks.
Yeah.
These are the boundaries set by God.
If you want. Maybe God doesn't want us to come to conclusions, right? Yeah, who knows? Who knows?
Without constellations, they wouldn't have civilization. They wouldn't be able to navigate around the world. They wouldn't even...
Or they find some other ways. Maybe at some point people find that their planet has a magnetic field or something. But their own galaxy still exists, so they can still look at the stars in their own galaxy. Because all of this only holds at scales about 100 billion light years. So that includes their galaxy, maybe a neighboring galaxy. Something like that. So that's sad. Yeah.
But even with like enormous amount of time, won't they still also expand away until a point that they're only like them?
The observable universe will be a solar system, or
Oh, you mean that the stars within the galaxy also move away? In principle, that's true, but we have been assuming up to this point that it's completely homogeneous and isotropic, which at small scales do not hold. So that means that all of our conclusions, now let's put it differently. Locally, there's all kinds of other gravitational effects that are much stronger than this expansion effect.
True.
Right? So they don't have to worry about stars moving away. And there's a second anecdote that I wanted to say. Remember that I told you that I read science fiction stories when I was little and such? Here's another one that I read, true story. Something about it's been a long time, but it was a small child. It was a story about a monastery. And then people came to this monastery and they found the monks over there and they asked the monks, so what do you do all day? And then the monk said, well, what we do is we count the stars.
I read it.
Yeah, do you know the story?
Arthur Clarke read.
Yes, exactly, yes. Do you know how it goes?
With the end of the world.
Yes, because they say to these monks that at the moment if they counted all the stars, this is the end of the world. And they keep on counting. And then these people who went there to ask them these questions, they fly back in their plane or something, and they said something like this. So, look at these stupid monks and their stupid medieval ideas on how the universe will end and such. And then they look up into the sky and then all of a sudden they see all the stars disappear. That's the story. Unfortunately, it's true. It's not because of the counting of the stars, it's because this is what the universe does, as far as we can tell, right now.
Is there any evidence that we've already witnessed this? Have there any been stars that people 200 years ago could observe, but we can't today?
No. Because it really depends on where this crossing point is. At one point, which one of the two takes over.
We're still well into there.
We're here-ish, but it's hard to tell without knowing this exact number, and we don't. That's one thing. There's a second thing, and that should be the end of cosmology, I think, but there's a second thing. What I've done here, by just adding these rows together, I've assumed that I can just take the row of energy, photons, the row of matter and the row of dark energy, and add them together and then solve this as this one big system. That's not allowed, mathematically, because it's a nonlinear differential equation. So that means you cannot just solve this one for dark energy and solve it for radiation and solve it for matter and then think that they move independently from each other. And that's what I've been doing now. I've solved it just for matter, just for radiation and just for dark energy, and then I assumed that these T relationships of rho and T are the same even if you put everything together. That would be true for a linear differential equation, but it isn't. And that means that there might be a way out. That maybe there is some combination by the nonlinearity of this differential equation that does not make that happen. And the answer is we don't know. It's active research at the moment.
So it comes closer and closer together until they crash instead of just being far away.
Yeah. Not. Well, no. That cannot be, because we saw last week that the only way that the universe can contract again is at the moment that you have a spherical universe. And as far as measurements tell us, we don't. We have a flat, yes. So whatever it does, it will always expand. Okay, questions? Yes.
Before we had we found out that lambda is equal to minus
yes.
kappa. And from there we said that the universe is expanding. I didn't really follow this thinking.
Okay.
How can we see that if lambda is equal to minus kappa, that has to expand?
Because we assumed that there were two. We assumed that you could write it as a sum of both. We assumed this one to be positive, and then we went through the calculation. We found that the only way that this can in total be a solution is when kappa is minus lambda. But if lambda is positive, then you have the sum of two positive exponentials, you have an expanding universe.
Okay.
This is where it came from.
And at the beginning I tried to solve this exercise as we solved the one with radiation and matter, so that we have not this type of differential equation like we have, but a differentials to the power of 2 divided by a is equal to second derivative of a.
Yes.
And then I used the argument you gave us that it should be like something like a times
t to the power or something.
Yeah.
Yes.
And then I did my calculation and it didn't work out. Afterwards I had 0 is equal to minus 1 also.
Okay, well, that certainly is not true. So if you find that is the
Yeah.
case, then your assumption was not correct.
But was in what sense my assumption was correct? Like, because I used another argument than you used, like
Okay.
E is
Well,
equal to E power.
unfortunately, I cannot tell from here. We would have to go through the calculation in detail. But I mean, it sounds like the steps, the program that you followed was correct.
Yeah, because it's like basically the same as the
Yes.
other exercise, just that the coefficient is not.
Yes.
It's 1 basically.
Yes. Again, I cannot tell from
Okay.
here, but your program is correct. There might be an algebraic mistake, or there might be
Yeah.
something else. I cannot
Or
tell.
could I have also used this step like
Yes,
this?
absolutely. Yes.
Okay.
Yes.
Yes, you said that experimental measurements suggest that the universe is probably flat, but then we also saw that if you take a local inertial frame, you can express any curved spacetime as a flat spacetime if you just look at it on a small enough scale.
Yes.
So where is this threshold for us to know when the scale is small enough so that we can exclude that it would be flat just because of the localness
I see.
of the frame that we are
Yeah,
considering?
I wasn't very specific about that. The question is, how do you know if you look close enough that the universe is actually flat, or that you just happen to be looking in a frame that is so small that it looks flat?
Yes, exactly.
Yes. We never went through it in detail, but I did mention it. There's this other tensor that you can make. It's called a Riemann tensor.
Okay.
And the Riemann tensor is a measure of the actual curvature. If that thing is 0, then you know that you really are in a Minkowski spacetime. If you find that in your spacetime metric the thing is not 0, this Riemann tensor, then that means that you are in a curved spacetime, even if it looks locally flat. So there is an actual thing that tells you if you are really in a curved spacetime or not. But we haven't gone through that calculation.
What if that piece of space is lower than the rate of curvature? Isn't that also an easy way to assess?
Well, yes. If you can find a measure of the intrinsic curvature and compare that to the typical size of that patch of universe that you're looking at, and you find that the patch of universe is smaller than the scale at which you expect deviations to happen, yes, you can do that too. That works. Any more questions?